Good morning, kids. We are going to discuss the ray optics in one shot. I'm your physics teacher, Sridhar sir. So, in today's class, we are going to discuss the ray optics in one shot. It's a very lengthy chapter, and lot of concepts are there to remember, and there'll be plenty of formulas also there and all. So, really, you have to put a lot of effort. It's not that something like, okay, fine, within 10 minutes I'll revise, half an hour revise. No, really some effort is there. And proportionally, the benefit you can see in exam, JEE means 2 questions and JEE advanced 2 or 3 questions. So here, how to plan. So first watch the video, what all I teach it, learn, understand all the concepts involved. And also remember all the formulas which you will encounter here and solve the PYQ. This is for JEE means last 2-3 years or 1 year, like what all you solve it, that will help you. Then those who are preparing for JEE Advanced, watch it, learn concepts involved, remember the formulas, and go through different types of numericals based on this. So you'll get exact perfect balance for JEE Advanced. The next question comes, how to plan this for JEE, like this ray optics in one shot. So we'll be first discuss about the laws of reflection. Agreed? Here, then the application of this is what the plane mirror. In the plane mirror, image formed by the plane mirror, then the magnification by the plane mirror, lateral inversion, then if object is moving, plane mirror moving, how the velocity of the image, then image formed due to multiple plane mirrors, more than 2-3 plane mirrors are there, how many images are formed, angle between the plane mirrors, how many images will be formed, then if the ray is incident at the plane mirror, then how to get the reflected rays, multiple mirrors are there, then rotation of mirrors, then acceleration of mirrors. So all these things will be analyzing in the plane mirror. And if a person stands in front of a plane mirror, what about the length of the mirror? So all this will come in the plane mirror. All simple idea based. The ray diagram is very important. Next again we'll discuss the reflection in spherical surface. In that the applications will be convex and concave mirror, image tracing, magnification. Then next if the object moves, if object is not on the principal axis, multiple mirrors, spherical mirrors are there, spherical mirror, plane mirror, combination. All these things we'll be discussing in the spherical mirrors. Then we'll go for the refraction at plane surface and Snell's law and its application. What we say, apparent shift, apparent height, apparent depth. Then double refraction, refraction slabs, silver slabs, slab and the concave mirror, slab and the convex mirror, slab and the plane mirror. All these things will be analyzing here. Then next we'll go for total internal reflection, TIR, and its applications. Then if a beam of light passes through a medium whose refractive index varies, then what method we should, how to trace out the ray in the way refractive in a medium where refractive index varies. Then we'll take the refraction at spherical surface. Then magnification formula, how to get the position of image. If a beam of light passes through a sphere, how to trace out the image. Then next we'll go for the lens maker formula, magnification, combination of lenses. Then afterwards we'll take the cutting of lens, then silvered lenses, then combination of lenses. If the medium surrounding the lenses change, if number of mediums in the lens changes, so this will be the lens. Then we'll take the deviation of ray by the prism. Then the dispersion, combination of prism, achromatic combination. All these things we'll be discussing in the prism and silvered prisms also. It will be like a very lengthy topic. There's no other choice for us. But once you understand, things are very easy. Okay, you know to get scared. Those who are preparing for means the methodology, watch this video, understand the concepts, remember the formulas involved, solve PYQ. Those who are preparing for JEE Advanced, watch this video, understand the concepts, remember the formulas, and solve more and go through more number of numericals related to all this, so that you'll gain confidence. But everything you have to draw the ray diagram. Remembering ray diagram you should avoid. Instead, try to learn how that ray diagram has come and you have to work out. So there's a basic strategy what we follow in the ray optics. So let me start like this. Now, first one will be laws of reflection. According to laws of reflection, the first law will be angle of incidence equal to angle of reflection. The angle of incidence equal to angle of reflection. Second one, the incident ray, reflected ray, and the normal all will lie in a same plane. This one, so this is a mirror. This part, this is a mirror. There's an incident ray. It gets reflected. The angle of incidence equal to angle of reflection. And what are the here? There's the angle. So what is angle of incidence? Angle between the incident ray and the normal, and the angle between the reflected ray and the normal will become angle of reflection. So what is the laws of reflection? Angle of incidence should be equal to angle of reflection, and the incident ray, normal, and the reflected ray, all they should lie in the same plane. A simple concept which you have to remember. Vector form of the laws of reflection. If the incident ray, if it is the plane mirror lies in a space, then incident ray moving in a space is incident at an angle. So let theta be the angle of incidence here. N cap is the unit vector directed along the normal. So then what is EI cap? Unit vector what is EI cap? Unit vector directed unit vector directed along incident ray. Then what about ER cap? Unit vector directed along reflected ray. And what about n cap? N cap is a unit vector directed along the normal. Then the angle, then the unit vector which is directed along the reflected ray is given by this formula, EI cap minus 2 times of EI cap dot n cap into this n cap. This will be a dot product of two vectors, will be scalar. Scalar multiplied will be vector, will be a vector. So again we'll get a unit vector. So if they give the direction of the unit vector which is directed along the incident ray and the normal, you can calculate in what direction the reflected ray will be moving. It's a purely formula based. You have to remember this formula, there's no other choice. Okay, fine. Where all the formulas are there, I'm just underline. I'll shade like this. Now the image formed by the plane mirrors. There's a plane mirror. There's a plane mirror. Then there's the object, real object. Okay, fine. The real object, it will send rays like this. They'll get reflected, and the reflected rays will enter into the eye, and the eye waterman will see as if these rays are coming from here. This will become the virtual image. Okay, fine. So you ask this eye where the image of this tree is there. It is at this particular distance. Suppose that there is a 10 meter. It will be visible at a distance of 10 meter. Now what will be eye will see? The reflected rays will enter into the eye. This is very, very important concept. These are incident rays. When eye will see the image of an object, when reflected or refracted rays enter into the eye, then that particular image formed by that particular, like an optical instrument, will be visible. There's a concept. There's a concept involved in the when a eye will perceive the image. I will visualize or I will see the image formed by the optical instrument. What are optical instrument? Mirror, lens, prism. When reflected or refracted rays enter into, this is a concept. Finish over that one. So where to see this image formed by the plane mirror, where you have to see, you have to be in the region where the reflected rays are present. Hope you got this. So this is a real object. It will, and what is a real object? Where the incident rays diverge from a point, that become a real object. And what do you mean by virtual image? If the reflected rays diverge from a point, that will become a virtual image. So this is one basic idea. Okay, I'll explain this one. So this is the real object. We have kept it here. The rays emitted by it will go. The rays emitted by it will fall on the mirror and will get reflected. Similarly here will be like this. Then we can almost trace like this. There's a reflected ray, real image formed by the, okay, sorry, this was the, next we have there's a virtual object. The incident rays are incident on the mirror. After reflection, they'll meet at this point. So it will form a real image. So what is the plane mirror? For real object, it will form virtual image. For virtual object, it will form the real image. Okay, sir, we are getting confusion. We want some little bit clarity. Next, we have the real object. From here, the rays are incident. They will strike the mirror. One day will strike the mirror at A. The second day will strike the mirror at B. After reflection, they'll be here. So here, if this is the angle theta 1, theta 1, theta 2, theta 2. The reflected rays will enter into I and it will form the image at this particular point. And from here, the reflected rays will diverge. Then it form a virtual image. When they enter into I, the eye, human eye will see that the image of this object, as object will be visible, image will be visible. When this image will be visible, formed by the mirror, when the reflected rays from the mirror enter into eye, then the eye is able to see the image. So for real object, virtual image. Similarly, for virtual object, these are the incident rays. So what are these? These are incident rays. They are. And these are reflected rays. So after reflection, the rays will converge at a point. So how the real image will be formed? If the reflected rays converge at a point, the point of convergence will be real image. What do you mean by virtual object? If the incident rays appears to converge at a point, the position of the point of convergence will be the virtual object. So there's one basic method here. So plane mirror for real object, virtual image, for virtual object, real image. How to trace out real or virtual image? Virtual image will be formed when the reflected rays diverge from a point. Point of divergence is the position of the virtual image. If the converging reflected rays will form a real image. The point of convergence will be position of real image. And there's a very fundamental, try to remember, very, very important. When a person is standing, so the height of the person, let it be h. Then there's a mirror. You will see this image and this height of object, this height of image. Then height of image equal to height of object. You will not see any magnification. Is object. And this will be its image. And height of the object will become equal to height of the image. So there won't be magnification. and your image is upright. So add foot, here also add foot. Your image is same size as you are, no magnification. What the magnification by the plane mirror equal to unity. Your image is at same distance as you are from the mirror. So object distance should be equal to image distance. Your left and right sides are interchanged in your image. So here this will be left hand. Then in the image open, this will become left hand of the image. Yes, there will be laterally inverted. The image, your image will be laterally inverted. Your image is behind the mirror, it cannot be seen on the screen. Your image is known as virtual image. Where is this is the image, no? And this is the object. Will be seen behind the mirror. Here. This is called like behind the mirror. So this is a general idea. Try to remember. Okay, now if this is the object placed here, how to trace out an image here? So here I'll send an incident ray. And it gets reflected. Similarly, I'll send another incident ray. And it will also get reflected by the mirror. Then I will trace out the image. So I'll extend back this. This will be our position of the image. This is X, this is X, this object, this is image. Okay, fine. Now, okay, this is a position, this object, real object. This will be the image here. This will be virtual image. These are the reflected rays. Red color reflected rays. Like this, you have to send the rays, and the reflected rays will diverge from a point, and the point of divergence will be the virtual image. Image means I here. Now, if object is kept somewhere here, then what about the image? That one. So again, we use the same method. There's the incident ray. Will get reflected. Then I'll send incident ray at some other point, and it gets reflected. I will trace it out the image. I'll extend back this reflected ray. So they will meet at certain point. This is a rough diagram. May not be according to the scale. This will be the position of our image. This is the position of the object. So how the rays are like this. This is incident ray, reflected ray. This is a second incident ray. This is a second reflected ray. So when I trace it out, this will be like this. Okay, fine. This everything is called like a field of view. If you want to see the image formed, you have to present in the field of the view. So what is the field of view? Where the reflected rays are present. So if you are present here, as you can see the image. If you are present here, you can see the image. If you are present here, you can. If you are here, you can't see it. If you are here, you can't see it. If you are here, you can't see it. Here you can't see it. So everything is called like a field of view. Here you can see it. So here you can't see. Here you can't see. So only in this region it will be visible. Similarly, this will be the field of view. Field of view, in short, we'll write it. So these are some generalized ideas which you should know it. It's all about sending how to calculate the field of view. Let the incident ray strike the edge of the mirrors. Then the reflected rays trace out. These are the boundaries of the reflected ray. No? In this region only all the reflected rays will be visible. Means this one. If you send any incident ray, it will get reflected. So the region in where the reflected rays are present, And if you stand in that region, the reflected rays will enter into eye, then you are able to visualize the image. So where the image is visible, that is called like a field of view. And this is one basic idea you should learn about the image tracing. Now the object is kept here in front of plane mirror, where you can see this is not the object distance. How the object distance you have to measure perpendicular to it. This will be your object distance. Then where the image will be formed at same distance will be higher. So how you can trace out the image. So for tracing the image again, the method will be you can send one ray like this. There's a reflected ray. Then send another reflected ray like this. Then after reflection, the reflected rays will diverge from a point. Okay, like this will be the image. This is the object distance. No, this is not the object distance. R is not object distance. Object distance and image distance should be measured normal to the plane mirror. Small basic ideas. Okay, sir, what is this plane mirror? Little bit image, you are telling something, putting dots, something. A simple idea. I'll keep one flower. This will be real example. We'll see the image of this flower. We are going to see the image of this flower. What about same thing? Suppose if it's having some color, we'll color it. You'll see the same color. There's a one simple ideas try to learn. Very important for you. So this is the object distance. The image distance also will be same. At what distance the object is present, the same distance the image will be present. And our object and image distance should be measured normal to the plane mirror. This is your plane mirror. This is a reflecting surface. Then if you want to trace out the image, you can do like this here. Okay, then this is your image, this is the object. Okay, like this is about the image. You stand in front of plane mirror, you'll get all ideas. Nothing bigger than this one. You can keep any object, its corresponding image will be the same size. This object, some shaped object like this, some E-shaped object is kept here. Then corresponding image will be this one, and this is the mirror. This is the mirror. Object distance should be equal to image distance. You look at this distance. This length should be equal to this. This length equal to this. This length equal to this, and this length will become equal to this. 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 No magnification, and there will be lateral inversion. If any shaped object, any irregular shaped object kept it, so there's a method of forming image here. Now we kept an object here. Like a rays emitted by the object will go and strike it here, mirror, and these are reflected rays. Corresponding its image will be formed. If you go and check it, the height of object will be called height of image. Then if object is kept like this, A, B, corresponding image will be A dash, B dash. The rays emitted by object after striking the mirror will enter into the eye. The eye will see the image here, not here. This is the object. And this is the image. Okay, kids, these are some generalized approach try to develop. And once again, I tell you, plane mirror is the conceptual part of the ray optics. Spend time here, understand ray diagram, how to trace out the image, everything. Then what happens? You can easily manage the coming topics. Okay, this will become fundamental for you. That's why I'm stressing some more general ideas. Huh? Next is the mirror and object are moving. So what is the basic method? As the object starts moving, the distance between the object and the mirror will be changing. Similarly, the distance between the mirror and the image will be changing. And we know object distance should be equal to image distance. So xmi equal to minus xmo. I'll differentiate this dxmi by dt dxmo by dt. So this will become vmi x minus of vmo x. So what is vmx? Vmx minus vx. Velocity of mirror with respect to x-axis minus velocity of mirror with respect to x-axis equal to vox. So we have to calculate vix. Vix is equal to 2 vmx minus vox. Okay, this will be the formula which you have to remember. What is vmx? Velocity of mirror with respect to ground, velocity of object with respect to velocity of the image. Okay, sir, what about the y-axis? What conditions are there for y-axis? Suppose if there's a mirror, here only let me just give the brief discussion. If the object moves along y-axis, then the image also will move along y-axis, and this distance will not change. So VIY equal to VOY. Similarly, if the mirror at rest or moving, doesn't matter. Mirror at rest doesn't matter. So VI equal to VOY. And there's a general formula. If object, mirror are there moving in a plane, then what method we should use to find out the velocity of image? So here Vix equal to 2 Vmx minus Vox. Vmx will be Vm cos alpha I cap. We'll define unit vectors. Minus Vox will be Vo cos theta I cap. Then what about VIY? VIY should be equal to VOY. VOY should be equal to how much it is? V naught sine theta by J cap. What about velocity of mirror along y-axis? That will not determine anything in the velocity of the image. Like this, now you can calculate the velocity of image Vix plus Vy. If object, mirror both are moving, then this is a method. Okay, sir, if they are accelerating, then we are going to differentiate this. Aix equal to 2 Amx minus Aox. This is for acceleration also. Then acceleration along y-axis is equal to Aoy. Whether we are moving with a constant velocity or varying velocity, this is a basic approach. Now, how to find out the number of images? Two plane mirrors are there. The angle between them is 90 degree. I'll keep the object at a distance A. Let's assume that the object is at a distance A from the mirror M1 and at a distance B from the mirror M2. Fine. So now we'll consider area. This incident ray will get reflected, and the reflected ray will diverge from this particular point. So this will form image Q2. Similarly, I'll send one incident ray towards M1. After reflection, the reflected ray will diverge from this. So this will be the image distance A. And here this will be image distance B. This object distance, image distance. Next, I'll send one incident ray. First it will strike mirror M2. Then it will get deflected from here. Then will be incident on mirror M1 and will get diverge from the point. So this will become 3 images will be formed. This is the image I1, this image I1, this image I2, this will be I1, I2. So if you check all this data, this will be B, A, this will be B, this will be B. This I1 will become object for M2 or I2 will become object for M1. If there is object distance, this will be image distance. This from retracing. So here what we do is like if there is there's not object. Now if the object is kept here, there's object here. Then what we do is like with respect to center of the intersection of the mirrors, draw a circle. Fine. So where are the mirrors? These are the mirrors. This is the mirror. Let me draw that mirror. This is the mirror actually. Okay, with this. Now the object O, the mirror, this CB will form image of the object O at this particular point. Similarly, the mirror CA will form the image of object O at P1. Then the P1 will become object for this mirror, it will form image, or this P2 will become object for this horizontal mirror, will form the image. So if you draw the circle with the center of the intersection of the mirrors, so what is this? This will be C here. C is the center of the circle of the mirror. Then where do all the images P1, P2 all, or say you can call them any name, will give it. Will give I2, same thing like I1, and this is I12. And where do all these images will lie on the circle? There's another method. You can just draw a circle and all the images I1, I2, I3 which are formed should be there on the circle. So for what is the condition? For any angle. And what should be the center of circle? Center of the circle should be intersection of the two plane mirrors. How many images formed here? 3 images. So now what is the angle between the mirrors? Angle between the mirrors is 90 degree. So therefore the number of images formed will be 3. So we'll generalize this one. Now if the angle between the plane mirrors, if it is theta, and if object is kept on the symmetric line, if the object is on the symmetric line, if the angle 360 by angle between theta, if it is even, number of images will be 360 by theta minus 1. This is one formula. Then similarly, if it is kept symmetric and angle between the mirror is theta and 360 by theta, if it is odd, then the number of images what happen, we are going to write it as 360 theta minus 1. Then if it is even, asymmetric and even, 360 theta minus 1 again. If the odd and asymmetric, 360 theta by minus 1. Asymmetric means like this here. The object is now suppose 60 degree. So if this angle is 20 and 30, then definitely what will happen here? This will become asymmetric. Now, there's a one generalized formula which you can remember, very, very useful for you. So we'll take one example, sir. No. So what is the angle between the mirrors? It is 60 degrees. How many images will be formed? So here I'll draw the circle with the center of the circle will be intersection of the mirrors. Then where all the images will lie on the circle. How many images will be? 360 by 60. How much it will become? 6. 6 minus 1 will be 5. Number of images will be formed will be 5. So all those images, they should lie on the circle. They'll ask you number of images only. That you can tell using this method. Next we have the angle between the mirror is 75 degrees and the object is not placed symmetrically. Then what is the formula? The angle between the mirrors is 75 degrees, so 360 degree by 75 will be 4.5. So the number of images formed will be only 4. This is a very simple thing, no need to do any research further here. And where all the images will be, they will be on the circle. One will be here, symmetric, I2, then I3, the other will be I4. Agreed? Huh? So we will take the next condition. If the two mirrors are held parallel to each other, then the number of images will be. Suppose this is object, we have kept it. First, the incident rays will go here, will strike the mirror A and will form the image I1. Then this I1 now will become object for the mirror B. The incident rays will go and strike, will form the image I2. This I2 now will become object for the mirror AB. So the incident rays will go and strike and will form I3. So like that here, we will get the images. Like this, multiple images will be formed. If they are very large plane mirrors, then you'll get infinite images between them. I'll just repeat here. P, first we'll start with this one. Only incident rays which are first striking the mirror A. So when the rays will strike the mirror A, it will form the image I1. Now after reflection, the rays will strike the mirror B. This I1 will become object for the mirror B and it will form the image I2. Similarly, this I2 will become now object for the mirror mirror A and will form the image I3. Similarly, I3 will become object and it will form the image I4. I4 will form the image and will become I5. Similarly, what about rays incident? If the rays first strike the mirror B, it will form image I dash. Then this I dash will become object for this, will become I double dash. And I double dash will become object for that. Then we can trace out the images here. So like this, if they're very large plane mirrors, infinite images. If they are finite, then some finite images will be formed here. Next, this will be, this object, this is a mirror 1 and mirror 2. First, the rays will strike the mirror 1. It will form the image. Let me call that as I1. Okay, fine. Now, similarly, the rays which are striking first mirror M2 will form the image. Let it be I1 dash. Dash means I'll represent for this. Then this I1 will become object for this mirror, will form the image I2. This I1 dash will become object for this mirror, will form the image I2 double dash. Then, okay, this I2 will become object for this mirror. It will form the image I3. Okay, this I2 dash will become object for this mirror M2. It will form the image I3 dash. This I3 will become object for mirror M2, will form I4. This I3 dash will become object for this, will become image I4 dash. So the images will be formed like this. All this I1, 1, 2, 3, I1, I2 are 3, I1, I2, I3 are like a 1 will be like this. Now, due to this, we are writing prime here. Means there are two set of rays. First, the rays which are striking the mirror 1. Due to that, we are showing the image I1, I2, I3, I4. If the incident rays which are first striking the mirror 2, they will form the images here. This is one basic idea. Now there is an object kept. So these are the plane mirror M1, M2 object kept here. I'll send an incident ray. After striking, the reflected ray will diverge from this. I'll get the image I1. Similarly, I'll send the incident ray. After reflection, the reflected ray will diverge from this. This is the image I2. Like this, two images will be formed. Only two images. Number of images will be 2. We'll take the next condition. Then similarly here, the incident rays will strike the mirror, will form the image I1. The incident rays will strike the mirror M2, will form the image I2. Number of images will be 2 only. There will be only 2 images here. Because again you send any ray, it will get deflected from here. Again you send any ray, will get deflected here. So how many images will be formed? Only 2. Next condition, there is an incident ray. It will strike here. We have to calculate the angle between the mirrors. So let this be angle between the mirrors theta. Then this ray is parallel to mirror M1, so this will be theta. Then angle of incidence should be equal to angle of reflection. Okay, then this is alpha, so this should be theta. Then after this, the ray will become parallel to the mirror M2. Then this angle should be theta, then this should be alpha, then this should be alpha. Then this should be theta. Then total this angle is equal to how much? This triangle, if you look at this triangle, 180 equal to 3 theta. Theta equal to 60 degrees. Like this we can calculate the angle between the mirrors. There's a one, if the rays are incident at the one of the mirror, after reflection will become parallel to the second mirror, then there's a condition. The angle between the mirrors should be equal to 60 degrees. Two plane mirrors are inclined to each other as shown. After 3 circles from them on the mirror M1 and finally retraces its path. Calculate the angle between the two plane mirrors. So first it will strike here 1, 2, so 1, 2, 3 and finally falls here. It will retrace the path. So for the retrace to path, so it has to be like this, 2 arrows, 3 and it will retrace the path. Then this is 30 degrees, so this will be 60, this is 30, 60, this is 90, this is 30, so this will be 30, this will be 90, this will be 60, this will be 30. Angle of incidence should be equal to angle of reflection. This should be 90, retracing path, so therefore this will be 60, this will be 30. So theta should be equal to how much? 30 degrees. So this is one basic condition. Like this, two mirrors will be there inclined at an angle. A ray of light will be incident. Some condition they'll give. And this is one basic approach. You have to just take help of angle of incidence equal to angle of reflection. Angle of, again here, angle of incidence equal to angle of reflection. Angle of incidence equal to angle of reflection. And you have to take help of the properties of triangle. Now, the rotation of mirror and the incident light. There's incident light, it will make an angle theta with a normal. There's a reflected ray and there's a mirror. There's a mirror. If I rotate the mirror to an angle alpha, this mirror is rotated. Then the incident ray, its direction will not change. But the normal, earlier it was making, normal means perpendicular to this. So definitely the normal will rotate. To what angle the mirror will rotate, to that angle the normal will rotate, alpha. Then this will become new angle of incidence, how much? Theta plus alpha. New angle of reflection should be theta plus alpha. Now compare the reflected ray, earlier it was making angle theta, now it will make angle theta plus 2 alpha. So how much the reflected ray rotated? It rotated by 2 alpha. So when you rotate the mirror by alpha, the reflected will rotate by 2 alpha. Then if the incident ray also rotates, then this is a one basic formula. Suppose I have the mirror. This is a mirror. So here I'm having the incident ray and there's a reflected ray. Just one small example we'll have here. This will rotate by 6 degrees. This will rotate by 2 degrees. How much the reflected ray will rotate? This will calculate. So this should be equal to 2 times of, this will be clockwise, no? The 6 degrees will be clockwise. The incident rate is rotating anti-clockwise. So therefore this you take it negative. So this will become anti-clockwise one will take positive, clockwise one will take positive. Anti-clockwise will take negative. This will become 12 minus of minus 6 will be 18 degrees. So the net will be 18 degrees clockwise. The reflected ray will rotate by 18 degrees clockwise. And this formula you have to remember, very, very important for you. A simple idea based thing. Next we have the torch light. This will send a beam of light which is incident on a wall. So as I rotate this torch light with an angle of omega, with what is the velocity of the spot on the wall? This is a basic thing. Let the torch light be at a distance d from the wall. Then from this triangle, tan theta equal to x by d. So as I rotate the beam, the spot will move along the wall. Velocity of spot that will move along the wall, not perpendicular to it. Then from this here we'll bring the constraint tan theta equal to x by d, x equal to d tan theta. We'll differentiate. Now why we should differentiate? Because as I rotate the beam, after some time the beam will come here. I'll take this one. We'll get a. Hope you are able to understand now. So this will be the velocity of spot. Here we are rotating this. How the spot will move along the wall only. So dx by dt vs equal to the theta will be varying, no? Earlier it was making theta, now this will become d theta. So definitely theta is varying. And what is the dx? This will become dx. So differentiating, so dx by dt will become v, d theta by dt will be omega, derivative of tangent secant square theta. So this will be the velocity of spot along the wall. Simple ideas, very, very important objective, either mains or advanced. Minimum length of a mirror so that a person can see himself completely. Let L be the length of the person. Then, so when the person is able to visualize himself, when he sees his foot and at himself through the mirror, and there's a mirror, we have the mirror. Now the rays emitted by his aids after reflection, if they enter into eye, then he is able to visualize his head. Then he will be able to visualize his head. Here we'll take some. Okay, this is the normal to the mirror. Now this will become theta 1, theta 1, theta 2, theta 2. So the rays emitted by head after reflection will enter into eye. The rays emitted by his foot after reflection will enter into the eye. And this will become similar triangle. So this length will be a constant. This length, let me call it as A. Then this length also will become A. This from high to head, let me call that as B. Or this will become 2B total. So this length will become B. So what is the length of the person? Length of the person will be 2A plus 2B, no? length of the person, length of the mirror, so what should be the height of the, what should be the length of the mirror? The length of the mirror should be half of the length of the, or half of the height of the person. The length of the mirror is equal to half of the height of the person. Then the person is will be able to see himself completely. This is one generalized thing which you have to remember. Okay, kids, we have the next topic, reflection at spherical surface. So how do that, what is the spherical surface, a convex and concave mirror, how they are constructed? I'll take hollow glass sphere. Here it is an hollow glass sphere having radius of curvature r. I'll silver the inner surface will be silvered, then this will become convex mirror. Similarly, if I silver the outer surface, then it will become a concave mirror. The inner surface will be available for reflection. Here outer surface. Then I'll cut this particular mirror at this point. This particular aperture, that is everything will become like a convex mirror. Similarly, this will become a concave mirror. This outer surface will be available for reflection. And the inner surface will be silvered here. The outer surface will be available for reflection. Outer surface silvered, inner surface will be available for reflection. Then the geometric center of this mirror will become pole. This center of curvature, line joining center of curvature pole will make a straight line, and this is a radius of curvature. This is called like a principal axis. So what is the pole? It's a geometric center of the convex or concave mirror. And C is the center of curvature, and the distance from center of curvature to the surface of the mirror will become radius of curvature. This is called like a principal axis, or just we'll call it as axis here. So then we'll take the image tracing. Then how to trace out an image here. So there's a concave mirror. This outer surface silvered, inner surface available for reflection. Ray 1, ray incident parallel to the principal axis. After reflection will pass through the focus. Okay, fine. This is a basic condition. Similarly, a ray passing to the focus after reflection will become parallel to the optic axis. Agreed? Then, if a ray incident at pole will get reflected symmetrically with respect to pole. So these are the image tracing. So to trace out the image formed by the concave mirror, I'll be using these particular rays. Agreed? And similarly, then for the convex mirror, the outer surface will be available for reflection. Inner surface is silvered here. There's a principal axis. A ray 1, which is incident parallel to the optic axis. After reflection will pass through the focus. Then if a ray is incident at the focus, after reflection will become parallel to the optic principal axis. Ray 2. If a ray is incident symmetrically at pole, will get reflected symmetrically. Then how this object image distance and the focal length? By mirror formula, 1 by v plus 1 by u equal to 1 by f, and the linear magnification is given by minus v by uf. What do you mean magnification? This is called linear magnification, height of the image by height of object. So we use mirror formula to find the position of object. We use the magnification formula to calculate the height of the image. This overall basic condition. Now concave mirror. If the object is at infinity, the rays will be incident parallel to the principal axis. After reflection, they should pass through the focus. Where the image will be at focus, sign the real. If object at infinity, the image will be formed at the focus and it will be real. Then how that focal length and the radius of curvature, they are related by this equation. I think everyone knows. F equal to R by 2. For concave mirror, it will be negative. For convex mirror, it will be positive. Because how the incident ray is like this, then the focal length PF will be measured opposite to incident ray. This will be the basic relation between focal length and the radius of curvature. Similarly, next one, if object is beyond C. If the object is beyond C, the image will be between C and F. Here I'll send one ray parallel to the optic axis. After reflection, it will pass through the focus. A ray passing through the center of curvature will get undeviated or will retrace the path. Both the rays will intersect here, will get the image. For object at beyond C, the image will be between C and F, diminished, real and inverted. There's a comment I have put it here. Similarly, if object is at center of curvature, image will be at center of curvature only. A dash. Then there's an incident ray. After reflection, it will pass like this. There's an incident ray passing through the focus. After reflection, will become parallel. Both will converge at this point. So therefore, object at center of curvature, image will be at center of curvature, same size, real and inverted. Then there's an object kept between C and F. The image is object is between C and F. First, the ray incident parallel to optic axis. After reflection, will pass through the focus. A ray incident normally on the mirror will retrace path. Both will intersect here. Will get the image. Where the object between C and F. The image is formed beyond C, real, magnified, and inverted. Next, if object is at focus, image will be at infinity. A ray, first this ray will be incident. After reflection, will pass to the focus. Other ray will retrace the path. Both the rays will become parallel. The image will be at infinity. Then, if object is kept between the focus and the pole, if object is kept between focus and pole, image will be beyond C or behind pole and will be virtual. So object between focus and pole, this object. What about the image? Image is virtual, erect and magnified and it will be behind P. So for concave mirror, for real object, it can form the real or virtual image. And this is a basic condition. Next, there's an object. It's a virtual object is kept here. You can see that one, the rays, there's an incident ray and there's incident ray. Here we'll show like this. After reflection, this will be after reflection. Okay, this one after reflection, a ray incident parallel to the optic axis. After reflection should pass through force. A ray incident at pole will get reflected symmetrically. Fine. Both these reflected rays will converge at a point, so this will be the image. What is the image? Image will be real. What about object? Object is virtual. So for virtual object, the image will be real, erect, and diminished. Height of the image will be less than height of the object. So what is not possible for concave mirror? Concave mirror cannot form virtual image for virtual object. So I'll just put it object and the image, real object, image will be real, then real object, image will be virtual. Okay, fine. Then if object is virtual, image will be real. Not possible. Virtual object, virtual image, not possible. Okay, only these things are possible for concave mirror. Now like this, you have to remember the data. Okay. So I have the concave mirror here. There's a concave mirror. There's an object. There's an object. A real object we have kept. There's a focal length here. Now we can control the radius of curvature and we can control the aperture of it. Okay, fine. Then this object, so I'll send the incident rays. Here, look at this ray. Ray, after getting reflected, will pass through it. Let me consider the three rays here. The ray, after getting incident parallel to the optic axis, parallel principal axis, after reflection will pass through the focus. A ray incident at pole will get reflected symmetrically. A ray passing through the focus after reflection will become parallel to the optic axis. Now where is the object? Object is kept like this here. No, you can see clearly. If object is beyond 2f, the image will be between here 2f will come, 2f and f. Here center of curvature will come, C, and the image will be real. This one will be real, inverted, and diminished as the object approaches at one point. if object at center of curvature, image will be at center of curvature, and the image will be real, inverted, and of same size. Again, the same rays, one ray parallel to the principal axis after it pass through the focus. Then you can see here object between center of curvature and focus. The image will be real, inverted, and magnified as the object approaches the focus. Look at the image will be at infinity. Then object between focus and the pole. Okay. Now you can see clearly. One ray parallel to principal axis after reflection will pass through the focus. Another ray incident at pole after reflection get reflected symmetrically. A ray incident here after reflection will pass through like this. So now this will be virtual image. These are the reflected rays. How the image will be real. So for real object, the image will be virtual. The image will be virtual, erect, and magnified. So the reflection, the rays will undergo reflection like this. If two objects are there, one object, I'll keep it here. The red color are corresponding to the object 2 will form for real object, real image. Object 1 for real object, it will form the virtual image. Okay, fine. So this is about the concave mirror. There's a basic idea. Agreed? Huh? The same thing here. Object. There's a center of curvature. There's a focus. There's a concave mirror. Here we have kept the object here. Look at the object as the size of the object. Now as I move this object, as I move the object, now you can see object beyond C, where the image between C and F will be real, inverted, and diminished as I move the object. And when the object is at center of curvature, object height and image height will be same. There's a ray will go like this, will get reflected. The ray passing through focus after reflection will become parallel. Then where these two rays will intersect, that will become the image. The image will be real, inverted, and of same size. When object is between center of curvature and focus, one ray here will send like this here. After parallel to principal axis after reflection passes through focus, other ray passing through focus after reflection will become parallel. Both the rays will intersect here. Here will get the image. The image will be real, inverted, and magnified. Now when the object is at focus, the image will be at infinity. If the object between focus and the pole, the image will be behind the mirror, and the image will be virtual, erect, and magnified. This is what basically happens for the concave mirror. Okay, got the picture, some diagram. So here I'll show it clearly like this. Here there's the object, you can see this, the image, and object at pole, the image will be at pole. Next one, if object is not on the principal axis, somewhere it is inclined here, then this length will form the object and corresponding will get the image. Then this will form the object height and corresponding will form the image. and we'll get the curved length. This is straight line AB. A dash B dash will be a curved one. Will be real. This is a real object. This is a real image. Then similarly, if object is kept between C and F, is having certain length, the image will be formed here. This will be image. Similarly, if object is kept between focus and pole, there is the object. The image will be virtual. Image will be formed here. There's a basic idea for the concave mirror, which you have to remember. Very, very important for you. Okay, kids, these are all small ideas. I'm sharing it. What is actually, sir, this image? What is that line? So just for to make you learn, there's a flower. So like this will be the object. There's a flower. You kept it. Then the image formed by this concave mirror will be between C and F. Object is beyond C. The image will be between C and F. Will be inverted, real, inverted, and diminished. This will be a real image. Similarly, for if the same flower is kept between the C and F, the image will be like inverted, real, inverted, and magnified. This will be this is a real object. Not only just some arrow straight line, we can discuss a general objects around us. You keep some pencil, flower. So we can have the discussion of this kind of, not something just mere some geometry. Any real objects around us can be kept nearby concave mirror and we can see it. Okay. Next we have there's the axis. Object at infinity, the rays are incident parallelly. This is a convex mirror. The inner surface is silver, the outer surface available for reflection. This is a pole, this is a focus, and this one is principal axis. The rays are incident parallel to the principal axis. After reflection, they will diverge from the focus here. And this will be the image form. If object at infinity, image will be at focus. If object is at some finite distance from the mirror, a ray incident parallel to the principal axis after reflection will pass through the focus. A ray incident at pole will get reflected symmetrically. Both these rays will diverge they'll intersect a point and they'll diverge from a common point. That will be the position of the image. A dash, B dash will be the image. So for real object, the convex mirror here will form virtual, erect, and diminished image. This is a real object. And the image form will be erect, virtual, erect, and diminished. The height of the image will be less than the height of the object. Anywhere you move this object, the conditions will be valid here. Now we'll take this one. So there's a real object kept here. Array incident parallel to optic axis after reflection will diverge from the focus. Array incident like at the focus after reflection will become parallel. Both they will converge at this point. This is the position of image. Now this is beyond 2f, object beyond C. Then real image will be between pole and focus. Similarly, object between 2f and f. Then also the image will be between pole and focus. If object is between focus and pole, then also the image will be between pole and focus. Agree this? The object at focus here. Then also the image will be between pole and focus. Okay, fine. So these are some basic condition. if object is at center of curvature, the image will be between pole and focus. So now image object from infinity to the point P, the image will be between pole and focus. There's one general conclusion we are making it. For real object, the image will be between pole and focus only and will be virtual, erect and diminished. Real object from minus infinity to pole, the image will be between pole and focus will be erect, virtual and diminished. There's a convex mirror. There's an incident tracer. There'll come. There's a virtual object. Then after reflection, they will diverge from a pointer, and this what will get here. Virtual image. So for virtual object, it will form the virtual image, and that virtual image will be inverted, magnified, and will be virtual. Object and the virtual object between F and C, the image will be beyond C. And there's one condition, try to remember it. Then similarly, one more is there. Convex mirror. If the virtual object is beyond C, the image will be formed between F and C will be virtual, inverted and diminished here. Height of the image will be less than height of the object. So what is possible for the convex mirror? Convex mirror. What all happens here? For real object and image. For real object, virtual image, virtual object, virtual image possible, virtual object, real image, as it is possible. For real object, real image, not possible. So I'll show this one. So now if the object is between pole and focus, virtual object between pole and focus, virtual object here, where it is between pole and focus. What about the image? The image formed will be real, erect and magnified. There's the incident rays. After reflection, they'll meet at a point and we'll get here a real image. The reflected rays, these are reflected rays. Okay, agree this. So there's a one basic necessity condition. So convex mirror, for real object, real image not possible, remaining all are possible. Next we have the convex mirror. There's a virtual object is kept here. There's a focus. The incident rays will come towards right here. Okay, now let me send the incident rays. Here we'll get the virtual, where the virtual image will be formed between the pole and the focus here. Now this is the incident ray parallel to the principal axis. After reflection will pass through the focus, and the ray incident at the pole will get reflected symmetrically where these two rays will diverge from a point. That will be the position of the virtual image. As I move this virtual object, you can see the virtual image will move between the pole and focus only. Will move between pole and the focus. You can see clearly. And what about the image? Image will be all the time erect, virtual, erect, and the diminished. And there's a one basic idea, you can check it here. Will be erect and diminished. There's one generalized thing which you have to learn here. Next we have the convex mirror. There's a convex mirror. This object we have kept, this image. So as I change the height of the object, you can see the height of the image will be formed, where the image will be between pole and the focus. Now as you move this object from far away towards the pole, where the image will move from pole to the focus only. Okay, fine. Once again I'm showing it here. As you move the object from far away infinity to the pole, the image, what happened, will move from focus to the pole. You can see clearly here. If object is near to pole, image will be near to pole. As object moves away from the pole, the image also will move away from the pole. And at far away, the image will be at infinity. I am unable to shift this distance further here. And there's one basic learning. So how to that image tracing will be? So first a ray parallel to the principal axis after reflection will pass through the focus. This one. Another ray incident here, like incident like this after reflection, incident at focus here, another ray after reflection will become parallel. So when both these will intersect here, we'll get the position of the image. Or another ray passing through the center of curvature should get retrace path. So when you reproduce it, where they intersect, there will be the position of the image. And there's a general idea which you have to develop here. If object at pole, image will be at pole only. If object not on axis of spherical mirror, there's a concave mirror, look at the object is here, not on axis. How to calculate the position of the image? We know object is between focus and the center of curvature. The image should be beyond C and should be like this is like extended object. The image should be beyond C, inverted, real and magnified. So the image we expect somewhere in this region. How to calculate these coordinates here? The x coordinate is given by the mirror's formula. Here the ray will be incident. So what about the ray tracing? A ray after reflection will come here. Another ray incident parallel to the principal axis after reflection should pass to the focus. Okay, this is a ray after reflection pass to the focus. This is a ray incident at the pole will get reflected symmetrically and both will converge at a point. So this will be the real image. We have kept the real object and a real image will be formed here. How to calculate? This is the xi, x naught object distance. How we measure? Opposite to the incident is moving towards left, the object distance measured towards right. So minus x naught equal to the focal length is here minus f. Xi is unknown thing, we'll calculate here. Substitute, already we have substituted here. So now solve it, we'll get the x coordinate of the image. The x coordinate of the image is given by this one. How to calculate the y coordinate? Magnification is given by minus of xi by xo. Yi, this will be yi. How to calculate the y coordinate of the image? Magnification by y naught. Substitute the y naught value, we'll get the y coordinate of the image. So now mirror formula to get the x coordinate, magnification formula to get the y coordinate. There's a general rule, try to remember it. Next we have the concave mirror. It is moving with a velocity Vm. This object and the object is moving with a velocity V0. Object is kept between focus and the center of curvature. We have to calculate the velocity of the image, with what speed the image will be moving. The image will be here, we have to calculate this velocity. There is a mirror formula 1 by v plus 1 by equal to 1 by f. As the object moves, the object distance will be varying, will not be constant. Similarly, this will be the image distance. So what will happen to image distance and object distance? that will be vary. So here, differentiating this minus 1 by v square dv by dt, my derivative of this 1 by u will be minus 1 by u square du by dt. What is dv by dt? Rate of change of position of the image with respect to the pole of the mirror. The mirror also is moving. So based on this, so we can write this as Vimx du by dt, velocity of object with respect to mirror along x-axis. Then this v square by u square will come here. Then Vimx, velocity of image with respect to mirror along x-axis, equal to velocity of image minus velocity of mirror, equal to Vomx, velocity of object minus velocity of mirror. Then solving for velocity of image is given by this formula. So what is this? This will be the velocity of image, velocity of mirror. This is the velocity of, and what is M? M stands for magnification. How to magnification? I should know the position of object in the image. We know the position of the object distance, we know focal length, we'll calculate the image distance. Then we'll get the magnification. Now, if object and image are moving, there's a basic generalized method which we should apply. Next here, an object is kept on the common axis of the concave mirrors of each of focal length. No, image must be on object itself. Then we have to calculate the distance d1. Then where this, suppose if this object is there's an incident here. After reflection will become parallel. Then the ray, what will happen? It has to form the image there only. So we know if a ray is incident, if object is kept where at the focus, let's assume that one, this, let it be focus. If the ray passes to the focus, after reflection will become parallel. If a ray is incident parallel to optic axis, after reflection should pass through the focus. Will extend like this. Okay, fine. So where the object should be known, the object. So this should be equal to focal length. So how much is d1? If d1 equal to 2f, then the image will be formed there only. So first this object will, this incident ray after striking will become parallel. And this ray will become incident ray after reflection will pass through the focus. Similarly, one ray you send like this. If the separation between the mirrors is 2f, then object image will be formed at object itself. Similarly, I'll increase the separation further. Then if this is center of curvature, then we know the ray will retrace the path. There's one more condition. If the ray passes through center of curvature, it will retrace path. Then what this distance will be? 2f and 2f. So d2 equal to 4f. Then the image will be formed at the object itself. And these are small problems you can expect. Now if the multiple concave and convex mirrors are present. How to trace out the image? Object is kept here. This will be the incident ray. After reflection, for object is there's a convex mirror. If object is kept on the left side of the mirror, the image will be formed between the pole and focus, so image I1. So from here the rays will go, get reflected, and the image will be formed here. So here we are discussing first the rays are incident on convex mirror, then on concave mirror. This is one of the condition. We have kept the object between the concave and convex mirror, and the rays are first striking the convex mirror. This will form the virtual image. This image I1 will become object for concave mirror, and it will form the real image. Okay, some simple ray diagram. Try to start with the small ideas like this. Condition. An object is kept here. AB is object. It is kept between C and F of this concave mirror. Let the focal length be F. Focal length of this, let it be also F. Or F dash, you write it. F2 or let it be F1. Where the object is between kept C and F. So where the image should be beyond C. So one ray parallel to principal axis, after reflection will pass through the focus. Other ray incident normally will retrace the path. So both these rays, they appear to converge at this point. So here we'll get the image formed I1 by the concave mirror. But what do this convex mirror will not permit it to converge here, will get reflected. And these reflected rays, they diverge from a point. So final image will be a virtual and will be erect, will be diminished compared to this. Then what is the total magnification? M1 into M2. Like this. So now we know the object distance x0. How to calculate this x1? This image distance x1. So for that I'll use the mirror formula, 1 by x1 plus minus 1 by x2 equal to minus 1 by f1. I'll substitute this x0 value. Why negative sign? Because the incident rays are towards left. And focal length you substitute, will get the x1, the position of the image I1, this one. Then this I1 will become object for this. Now this will become the object distance x1 dash. So substituting in again the mirror form the x1 dash, this will become positive. Now this will be the all the distance I'll measure from pole. The reflected rays are moving towards left now. So this will become now object distance, which is measured in the direction of the incident ray. So will be positive. Focal length positive. I'll calculate the x2. I'll get the position of the image. Then the magnification here M1 will define it as minus of x1 by xo. Substitute x1 and xo with sign. Similarly, magnification is defined by x2 by x1 dash. Substituting, we'll get the height of the image. A dash, B dash also we can calculate. If multiple concave, convex mirror or two concave mirror, this approach is what you have to develop. A dash, B dash equal to M1 into AB. A double dash, B dash equal to M2 into A dash, B dash. These are the formulas. And the total magnification is product, not sum. A convex mirror and a plane mirror, an object is kept so that no parallax with the image formed here. The plane mirror will form an image, the convex mirror will form an image, and both these images should merge at a common point. For that, what should be the focal length? So a plane mirror, it is kept at a distance 30 centimeter. The distance between plane mirror and convex mirror is 20 centimeter. He was asking what should be the focal length, so no parallax. Between the plane and convex mirror. So the ray incident on convex mirror will form the image at I. the ray incident at plane mirror will form the image at I. And we know for the plane mirror object distance should be equal to image distance. So now we know that 20 centimeter, the image distance from the pole will be 10 centimeter. Okay, agreed. And what is the object distance? Is 50 centimeter. Then towards right should be taken as positive for convex mirror. So plus 10 image distance minus 50 object distance. Focal length we don't know, we'll solve it. So like this, the combinations of mirror, concave, convex mirror and plane mirror will come. This approach you have to develop. An object is placed between a plane mirror and a concave mirror of focal length as shown. Find the position of image after two reflections. So there's an object is kept here, you know, between the plane mirror and the concave mirror. Okay, now what is the rays here? So first reflection, the rays will be incident on the concave mirror. Then after reflection, they wants to converge at point I1, but the mirror will not permit. What the mirror will do? Mirror will reflect it. And this will be the final image formed here. Then we use formula 1 by pi1 po. For the rays incident on the concave mirror, towards right will be positive. The object distance, how much it is? Minus 20. Focal length we know 15 minus 15. So all will get pi1. Pi1 how much we are getting? Minus 60 centimeter. This is 30. This will be 30. This I1 will become object for the plane mirror. Virtual object, it will form the real image. The I2. So this will be 30 centimeter. If virtual object 30 centimeter, the real image will be at a distance of 30 centimeter. The final image will form at the pole of the concave mirror. So like this, mirror, plane mirror, concave mirror. Two concave mirrors, two convex mirrors, or plane mirror and convex mirror. Like this combinations will come, you should know this one. Think about ray diagram, very easy. Next we have the superficial magnification or what you can call area magnification. Some structure is kept here, is having some plate which is having area of cross section. If the object is kept between focus and curvature, center of curvature, the image will be beyond C, and will be erect, magnified, and will be real. Will be inverted, real, inverted, and magnified. Then what is the area magnification given by V square by U square? What is U? The distance at which the surface object, the distance at which object is from the pole. There's object distance. What is V? The image distance of the image formed by the concave mirror. So I think I use the mirror formula. I'll get the V value, then I'll get the magnification, then the area magnification is given by V square U square by area of cross section of the plate. This is called like a superficial magnification. Good morning, kids. The next topic will be having the refraction at the plane surface. Here. So first we'll start with the Snell's law. When a ray of light moves from one medium to other medium, the ray of light will bend. So here, how the speed of light and the refractive index of the medium, they're related like this. Speed of light in the first medium. Here it will be moving with the speed v1. In the second medium, the speed of light will be v2. Then the speed of light is equal to, in any medium, equal to speed of light by refractive index of the medium. Similarly, speed of light in second medium equal to v2 equal to c by n2 here. Then from the Snell's law, so what is the equation we can write here? Like n1 sin theta 1 equal to n2 sin theta. This is a basic Snell's law. Then further, what is the n1 refractive index? C by v1, c by v2. So this will become sin theta 1 v1 by sin theta v2. In terms of speed also we can express here. So when the ray of light moves from one medium to another medium, it will bend. This bending of ray of light will call it as refraction. If there are multiple mediums are there, like I have here the multiple. So here this is the boundary, this is a normal, this is the angle of incidence. The ray is incident, it will bend. It is moving from rare to denser, so it will bend. Then theta 2 will be angle of refraction. Again encounter one more boundary. Theta 2 will be angle of incidence. Theta 3 will be angle of refraction. Then we can write here the Snell's law, n1 sin theta 1 equal to n2 sin theta 2. n2 sine theta 2 is equal to n3 sine theta 3. We'll get equation like this. If n1 equal to n3, then we can write here theta 1 equal to theta 3. This is a condition. Okay, if n1 equal to n3, then theta 1 will become equal to theta 3. Provided this is a condition. Then this will be valid. Next one, we have the Snell's law in the vector form. There's a boundary. There's a refractiveness of medium mu1. There's a refractiveness mu2. There's a normal. This incident ray, it will make an angle theta 1 with a normal. Theta 2 is the angle of reflection. E1 cap is the unit vector directed along the incident ray. What is E2? E2 cap is the incident ray directed along the refracted ray. Then the same Snell's law in the vector form is given by mu1 E1 cap minus mu2 E2 cap equal to mu2 cos theta 2 n cap minus mu1 cos theta 1 n cap. N cap is unit vector directed along the normal. E1 cap is unit vector directed along incident ray. E2 cap is refracted ray directed along the refracted ray. Then mu1 sin theta 1 equal to mu2 sin theta 2. So this particular thing, if the vector form is there, you can remember this one. Very useful for you. Next, after this, if there's an incident ray, angle of incidence theta 1, refractiveness of medium is mu1. Here refractive index of the medium, there's a refractive index, it is called as. So this is called a refractive index of the medium. So this will be mu1 sin theta 1 equal to mu2 sin theta 2. Then here mu1, as the incident ray rotates, the angle theta 1 also will vary with the time. So this will become cos theta 1 d theta 1 by dt, mu2 cos theta 2 d theta 2 by dt. This will become mu1 cos theta 1 omega 1. Okay, fine. Like this we can calculate the omega 2. This is the angular velocity of the refracted ray. Now next we'll discuss about the deviation. How to calculate how much the ray will get deviated. This is a normal, there is a refractiveness of medium mu1, there is a mu2, this is the angle of incidence, this is the incident ray. The refracted ray will make angle of refraction r, that one, with the normal. Then the ray of light is moving from rarer to denser. This is the rarer. When a ray of light moves from bright to denser, the refractor will bend towards the normal. Then what is the formula? The formula will be same thing, mu1 sin r equal to mu2 sin r. Then there is a deviation. Actually the incident ray wanted to move in this particular path. It is now deflected here. So deviation will be I minus r. This angle will become I, no? What is this deviation equal to? I minus r. If a ray of light moves from bright to denser, the deviation will be I minus r. Similarly, if a ray of light moves from denser to rarer, this is a denser medium, this is a rarer medium, then the deviation is given by r minus I. Then the same Snell's law you can apply it. When a ray moves from denser to rarer, the ray will bend away from the normal. This is a normal. Then the Snell's law will be mu d sin I equal to mu r sin r. All these small ideas of Snell's law you must be very careful. Why do that bending of ray of light? Due to change in speed. And what quantity will remain constant? The frequency. The frequency of the wave will not change. As the wave moves from one medium to another medium, frequency will not change. What about the speed here? Speed v1, speed here will be v2. Lambda wavelength also will change. Lambda 1, lambda 2. The frequency remains same. Next concept is apparent depth. There is a swimming pool. Some object is kept in at the bottom of the pool. Let this be O. When the person views it outside the water, for him, what when the object will appear near to the surface. This actual depth here, but it will appear here. This is called like a apparent depth. Though object here, it appears to be here. So how to calculate this apparent and actual depth here? For that, how do actually the rays will propagate here from this object? This incident ray will undergo refraction, will enter into the eye. Now, this object, it will emit the rays, this incident ray. After refraction, as it will enter into the eye. Then, for this eye, from where the rays are coming, as if they are coming from here. So the same object now will appear to be here. So we'll call that as image. So when the person will see the object, when the refracted rays enter into the eye, the refracted rays from where they are coming as if from here. So the same object which was at a depth HR will appear at a depth HI, or apparent depth, what we can call here. So then here we'll apply the Snell's law, like a mu1, like a n2 sine theta 2 is equal to mu1 sine theta 1, solving this for paraxial rays. This point C will be very near to it, sine theta will become tan theta, solving, I'll get here. So apparent depth is equal to HR, the medium in which object is present, into the medium in which the viewer is present. Real depth by the refractiveness of medium where the object is present into refractive medium where the viewer is present. If viewer is present in here, this n1 will become equal to 1. So apparent depth equal to real depth by refractive index of the medium. This is a generalized formula, try to remember. If there are multiple liquids are there, I kept a coin. This one, and this particular beaker is filled up with 3 liquids, N1, N2 and N3. We have to calculate the apparent depth. Then what we do is like the apparent depth will be the depth due to individual liquids, due to the liquid 1, liquid 2, liquid 3. Then add up apparent depth to individual liquids, D1 by N1, D2 by N2, D3 by N3. Solve it, we'll get the object. This particular coin, though it is here, for this human eye, it will be visible here. One more example, if there's an object or a coin kept in a cup, the person is waving, this coin will appear here. Though it is kept at the bottom, but it's going to appear at this particular point. Then here I'll increase the level of liquid. What will happen? Definitely the apparent depth will change. Earlier what was the real depth? Real depth was this much, and this apparent depth. HA dash equal to HR dash by mu, and HA equal to HR by mu. As your real depth changes, apparent depth also will change. The same coin now will appear still more at certain distance here like this. Hope you are able to understand now this one. So the apparent depth depends upon the real depth of the liquid. How to change the real depth of liquid? By changing the level of liquid. Just some general discussion I brought it here. Next we have the bird here. It is in air and it is viewed by a person who is there in the water. The rays emitted by the bird will undergo refraction, will enter into the eye. For the eye, what happens? The rays are coming out as if from the point eye, and this is the point to object, you can take it. They are coming as if from here. So the same bird now will not appear here, will appear at this point. So this is a real height, this is apparent height. Then according to the formula, the apparent height is equal to mu2 HR by mu1. If mu1 equal to 1 and mu2 equal to mu, the apparent height equal to mu HR. The bird will appear further for the eye. Not be nearer, it will be further. Okay, now there's a bird. It is at a height 6 meters from the ground, and we have the fish which is at a depth 0.8 meter, 0.8 meter from the, I'll make it 8 meter rather than this, I'll make it 8 meter. I have the bird which is at a height 6 meters from the boundary. Then it is moving down 3 meters per second. I have the fish which is at a depth 8 meters and it is approaching the boundary with a speed 2 meters per second. Now I want the distance of fish as seen by bird. Distance of fish as seen by the bird is at what distance? 6 meters. The bird is at this meter. What is the real depth of the fish? 8 meters. So 6 plus this is 8 by mu of the water. So this will become 8 plus 4 by 3. 12 meter. Where the bird actually it will appear at a distance of 12 meter for the fish. For the fish will appear at a distance 12 meter for the bird. Similarly, speed of fish as seen by the bird. So these equations only. Okay, we'll substitute symbols. The same thing. First, we'll take the symbol x plus y by mu. This will become 6 plus 8, 4 by 3. Then speed of fish as seen by the bird. I should differentiate this. This will become derivative. What is a dx by dt? Dx by dt is decreasing. Speed is decreasing. So it's decreasing. So therefore minus 6. Then dy by dt is also decreasing. So this will be minus 3. Speed of the bird, dx by dt will be minus 3. dy by dt will be minus 2 because y is decreasing. Y increasing, velocity will be positive. If the fish moves away from the boundary, that velocity you should take positive. If the fish moves towards the boundary, you have to take it negative. Any distances decreases, dx by dt, dy by dt negative. Any distance increasing, there will be positive. By 4 by 3. This will be minus 3 minus 3 by 2. 6 minus 4.5 meters per second. That is the speed of the fish as seen by the bird. Similarly, distance of the bird as seen by fish. B means bird. F means fish. Then the fish is at what distance from the boundary? At a distance y. Then the bird is at a distance x, mu x. So this will be y will be 8 plus 4 by 3 into mu. Okay, this x is 6 meter. 16 meter it will appear. Then the speed will be given by y dash plus mu into x dash. dy by dt decreasing minus 2. dx by dt decreasing minus 6. Minus 10 meters per second. Okay, there's a one basic method. Try to follow. Very, very important. When should take positive? If this x decreases, dx by dt negative. X increases, dx by dt positive. There's a convention. X increases, dx by dt, or x decreases, dx by dt, or this one will be negative. The distances from kinematics, all this convention. Next we have there's a tank. The water is filled up to a height b. A fish is located at a distance c. Then above the water surface, an human eye is located at a distance c. Then the bottom of tank is silvered. Then two rays will be there. One, directly the rays emitted by fish will incident at the boundary, will undergo refraction, enter into that. The next set of rays, first they strike the mirror, get reflected, then refraction, then enter into the eye. Then two images will be seen, two fishes will be seen, one due to direct rays, other due to indirect rays. Agreed? First the eye will see the fish directly. At what distance the eye is from the boundary? At a distance A. So distance of fish as seen by eye directly. This will be A plus. Then what is the real depth of the fish? B minus C by mu. Okay, great. This one. Similarly, the eye what one will be, eye is also will treat like some object that will be seen by the fish. In that case, distance of the eye as seen by fish directly. Now the rays emitted by the eye will undergo refraction, will enter into the fish. Then at what distance the fish is from the boundary? B minus C. What is the height? Height will be A. Then this will become mu A. These are apparent depth and apparent height formulas. Okay, now distance of fish as seen by eye indirectly. What do you mean by this? Actually, the fish, what will happen? The rays emitted by fish will strike the mirror, will undergo reflection, will form the image f dash, and these reflected rays will undergo refraction, will enter into the eye. Okay, agree this. So this will be at what distance the mirror will form the image of the fish at a distance C. So therefore now the distance of fish as seen by at what distance the eye is from the boundary A. Now this will be B plus C by mu. Here what is present here, there is no water, but the image will be at a distance of how much? B plus C from the boundary. This will become B plus C by mu. Similarly, distance of eye as seen by fish indirectly. The rays emitted by the eye will undergo refraction, will undergo reflection. Then the image will be formed. That image will be seen by the fish. So what is actually happens? The mirror will behave like some object and it will form that image. The mirror, you treat mirror is looking at the eye. At what distance the mirror is? At a distance B. The mirror is at a distance B from the boundary. And what is apparent height? Mu A. So here it will be B plus mu A. That particular thing will be form the image. Then plus C. Because the fish is at a distance from the mirror, no? So the distance of the eye as seen by indirectly means we have to write in this way. Next we have the topic apparent shift due to a slab, or what you can call double refraction. I kept object 2 here. The ray here will undergo refraction, and after refraction form the image I1. Now this ray will undergo refraction, will get here. So here there's a one ray. Next we have the okay, fine. The next one is these are the rays. So remaining all are this one. So these are the incident rays. This object is a real object. It will send the rays. Will undergo refraction. Will form the image I1. Then again it will undergo refraction, and finally the image will be formed at I2. So now this refracted ray will enter into the eye. And for this eye, the object instead of at O will appear at I2, and there is a shift. This is called like a shift. Fine, in this way we define it here. Let the T be the thickness of slab, mu the refractive index, the refractive index of surrounding medium, let it be A, which is equal to 1. Okay, now what is the shift produced is equal to apparent shift equal to thickness of the slab 1 minus refractive index of surrounding medium by mu. Since the surrounding medium will be air, the apparent shift will be 1 minus 1 by mu. And in what direction the shift will be there? In the direction of incident. It's very simple here. The ray will undergo refraction and the image will appear. Means for this eye, the object will not be at this point, will appear near to the eye. And how much it got shift? Equal to t into 1 minus mu. So we'll write down this formula. There's a shift. And in what direction the shift? Shift will be in the direction of incident ray. There's the thickness of the slab. If surrounding medium is mu naught, that value you substitute here. And the shift will be always in the direction of incident ray. Ray of light passing through the slab will undergo refraction. And again it will undergo refraction. There's a one refraction. Then again it will undergo refraction here. Again it will emerge out, will undergo refraction. So if you finally look at this one, there's an emergent ray, there's an incident ray, and there'll be parallel. There won't be deviation. The deviation by the slab. The emergent ray will be parallel to the incident ray. This is the incident ray. And what about this? This is the emergent ray. And the emergent ray will be parallel to incident ray. And this is the lateral shift. This lateral shift depends on these things. L is equal to t into sine of I minus r by cos r. There's a formula you have to remember, very, very important. This lateral shift. Earlier we were discussing the apparent shift. This is called a lateral shift. The shift of what? The shift of the ray. What is L? L is the lateral shift of the incident ray. This one, this we are discussing. T is the thickness of slab, I is the incident, angle of incidence, R is the angle of refraction. So you have to remember, very useful for exam. If you have the multiple slabs here, slab, okay, is having refractive mu1, thickness T1, mu2, thickness T2, a third slab, refractive mu3, thickness T3. Surrounding medium, the refractive index is mu naught. There's a human eye which is going to see the object. So here object we have kept, real object it is. Where do it appear? According to the formula, thickness of the first slab 1 minus surrounding medium mu naught by mu1. Thickness of second slab T2 1 minus mu naught by mu2. Thickness of third slab 1 minus mu naught by mu3. Algebraic sum of shift due to individual slabs, take it, then that will be shift. So the object which is here will appear near to it. The same object will appear at this particular point. This will be the image. This will be virtual. If you have this eye, the object will not be here, will appear at this particular point. This multiple slabs, there's a condition you have to remember. Next we have the silvered slab, an object O, there's a flower, there's a real object. Where do its image will be formed? First, the rays will pass through the slab, will undergo double refraction. So here, for the slab, for the mirror, the object will not appear at O, in fact will appear at O dash. So what the shift equal to thickness T? T is how much? 6 centimeter. Refractive index of slab 1.5. Substitute, we'll get the shift as 1.5 centimeter. Then the object was at a distance 20 centimeters. Now will appear 18.5 centimeter from one end of the slab. For the mirror, it will appear at this point. Now, the mirror will see not the real object, will see the apparent object O dash. The same object will appear here. It will form image corresponding to O dash. So what is the object distance? 8.5 plus 6 will be 24.5. So the mirror will form the image at 24.5. But after reflection, again the rays has to travel through the slab. Again has to travel through the slab. So therefore, again the shift will be produced. So final image will be at 23 centimeter from the silver surface. Small idea, try to remember. Next we have the object is there in the slab. This is like virtual object. Where do it appear? So the ray will undergo. So we have to calculate the shift. The shift produced by T into 1 minus 1 by mu. The surrounding medium is air. Thickness of slab 6, 1 minus 3 by 2, 2 by 3 will be 2 centimeter. So where the image should be in the direction of the incident ray. So the image will appear at this point. So what is actually happens to the ray? The ray will undergo moving from right to denser will bend. Moving from denser to rarer medium. Will move from denser to rarer medium, so should bend away from the normal. So here it will be the image will appear at this particular point. The boundary itself, the shift will be produced here, and it will be real image. Virtual O is a virtual object. What about I? I is a real. Okay, agreed. There is some condition. Next, I'll bring the slab and concave mirror. So an object is kept here. Then there's the slab. The rays first will strike the slab, will undergo double refraction. Then the shift is given by this particular formula, T into 1 minus 1 by mu. For the concave mirror, the object will not appear at O, will appear at O dash. Then how much of shift will be? O dash. Then corresponding to O dash, the concave mirror will form the image I dash. Then use the mirror formula to calculate the Pi dash. Then again the reflected rays, again they'll pass through the slab, will undergo double refraction, and the shift will be in the direction of reflected ray. So here the final image will not be at I dash, will be at I. Again, what is the shift? The same formula you can apply it. So like this, the final image will be real. Here we have kept the real object, and the final image will be real. Because from here, lower set of incident rays you consider, the reflected rays, the refracted rays converge at a point. So this will be real image. Okay, fine. I will take that next, convex mirror. Now slab and convex mirror. So there's a convex mirror and there's a slab having focal length f. The object is kept here. The rays will undergo double refraction, and for the convex mirror, the object will not be at O, will be O dash. I'll apply the mirror's formula, I'll substitute all the things. I'll calculate the position of the image. The image will be formed at I dash. Then the reflected rays again they'll pass through the slab, and finally the image will be formed at I. This will be the final image. This will be virtual. So what that slab will do, whenever a ray passes through the slab, will undergo double refraction. That's a basic idea. So here the ray will undergo double refraction, and then there will be incident on the concave mirror. So where the rays, the incident, these rays, they are not coming from O, coming from O dash. So therefore for concave mirror, the object will not be at O, will be at O dash. Agreed? And after reflection, again the rays will undergo double refraction, so the image will not appear at I dash, will be at I. This will be the final image. I have a cylindrical vessel whose diameter and both are equal to 30 centimeter. Okay, agreed. Huh? Then a small particle piece placed at the bottom. The eye is positioned so that it is able to see only the vertical part. This part is not visible. So this part will be visible. Or you can call this A, B, P1, P2. So what I will say, AP1 is visible. Side wall, AP1 is visible. And ACBP2 not visible. ACBP2 is not visible. Now I'll pour water so that the point P should be visible. So what level? The height I should find. Now if you could look at this one, P1AP. If you ask your eye, it will say that P1AP is visible. PB, P2 not visible. So how it is possible? The rays emitted by this will undergo refraction, will enter into the eye. Now we know this angle was equal to 45 degrees. We know theta 2 how much it should be equal to 45 degrees. Then applying sine mu sine theta 1 equal to, this is a 1 into sine theta 2. I'll get the theta 1. Then here some basic mathematics will apply it. This length L minus h, tan theta 1 from here, this triangle tan theta 1 equal to x by h. Then tan theta 2 is equal to L by L minus h. Theta 2 45 degrees. Solving this will get the expression for h. Fine. So this is about the refraction. So by pouring the water now, this whole part will be visible. Again, anyway, this part will not. If you pour more water, even this part also start getting visible. Next topic we have the total internal reflection. Here, there's an incident ray. It's moving from denser to rare medium. The ray will undergo refraction. Then what is the formula? We'll write N1 sine theta 1 equal to N2 sine theta 2. This is the angle of incidence, angle of refraction. As I increase angle of incidence, the angle of refraction also will increase this naturally. So I'll increase this angle of incidence. The refracting angle also will increase. And at one particular angle of incidence, the refracted ray grazes the boundary. And this angle, it will make 90 degree. So now, the angle at which the refracted ray grazes the boundary, that particular angle of incidence, I'll call it as critical angle. So N1 sine theta c is equal to N2 sine 90. So sine of critical angle equal to N2 by N1. Critical angle equal to sine inverse of N2 by N1. What is N2? Refractive index of the rarer medium. What is N1? Refractive index of denser medium. So the critical angle is equal to sine inverse of refractance of rarer medium to denser medium. Mu r equal to 1. Mu d equal to, let it be mu. Then the critical angle formula will be sine inverse of 1 by mu, or sine c equal to 1 by mu. The ray will get totally internally reflected. No refracted ray in this medium. All the energy will be reflected back. This is called like a total internal reflection. What are the examples like? There's a fiber optic cable. The ray is incident. Here it will undergo TIR. Again it will undergo TIR. Again it will undergo TIR. Like that, by successive TIR, the ray what will happen? Will traverse a length of almost 200 or 200, 500 or 10,000 kilometers of the cable length without loss of light. This is what we use for the fiber optic communication. if it undergoes successive TIR, because due to total internal reflection, no loss of light. So hence the light will propagate from one end to other end. Then here, the ray of light is incident, will undergo refraction, will undergo TIR here. Again the ray of light here will undergo TIR, again will undergo TIR and will emerge out. This is what happens in the diamond. Then mirage. So how that mirage is formed? The light emitted by this palm tree will undergo refraction because of the variable density. It will undergo, the light will bend, will enter into the eye. Now these rays of light, they appear as if they're coming from here. So rather than seeing this, the person is able to see also its image. The object is here, it will also, this will be visible. This is called like a mirage, we'll call it. Why do the ray of light will bend? Because of the variable refractive index. With a fiber optic cable, here the ray of light is incident, will undergo refraction. Let the angle of incidence here be I. Here the angle of refraction, let it be alpha. Then the ray will be incident here. Here the refractive index of the core, let it be N1. Refractive index of the cladding, let it be N2. The ray here will undergo TIR. If the angle of incidence just greater than or equal to critical angle, the ray will undergo TIR. Again, if this angle is theta, this angle will be theta. Again, the angle of incidence just greater than critical angle will undergo TIR. Like that, it will undergo successive TIR. And the ray of light will move from one end to another end without loss of light. So here there is a core. There is a cladding. So at point 2, the angle of incidence is I, and the angle of refraction is alpha. Here at point A, the angle of incidence, let it be theta, which is greater than or equal to critical angle. Like this we are discussing now. Now we'll apply it here. 1 into, applying the Snell's law at point 2, 1 into sine I equal to N1 into sine alpha. Angle of refraction is alpha. Then here from this triangle, alpha plus theta 90, theta equal to 90 minus alpha. Then here, applying this, here sine theta is equal to sine of 90 minus alpha. What is sine theta? N1 sine theta. Here N1 sine theta should be equal to N2 sine 90, just equal to critical angle, it is a condition. So therefore sine theta equal to N2 by N1. Sine of 90 minus alpha will be cos alpha. So N2 by N1 equal cos alpha. Cos alpha, what you can write it as root of 1 minus sine square alpha. Sin alpha, what you can write here, sine square I by N1 square. Solving this equation further, N2 is equal to N1 square minus sine square I. So N2 square equal to N1 square minus sine square I. So I'll get expression for I. So any angle, any incident ray whose angle here less than this I will enter into the core, will undergo successive TIR. This is a condition. Any ray which is entering at the core, if the angle of incidence less than this, will undergo successive TIR here. Any ray entering core at O satisfies this equation will undergo successive TIR. Okay, this is a basic idea of the fiber optic cable. We'll discuss the concept of variable refractive index. Okay, then here I am choosing a medium where the refractive index will vary along x-axis here, will vary along x-axis. The ray will enter the origin, at O. There's origin we have chosen. Here let this be air. The angle of incidence, let it be theta naught. Here as this is air, so here the ray will bend like this. Why it will bend? First of all, what is the mu? It varies along x-axis. So how the boundary? The boundary will be parallel to the y-axis. If the refractive index increases along x-axis or varies along x-axis, the boundary will be parallel to y-axis. Okay, fine. Now the ray will enter, and x-axis will be normal everywhere. You can draw at any places. The x-axis, the line parallel to x-axis will become normal at point P. And this is a boundary, this will be normal. The ray water pen will bend because it is moving from rarer to denser, because as you move the mu will increase, so the ray will bend towards normal, so it will be bending like this. It will bend here. Then okay, after this at point P there's a boundary, there's a normal. Let theta be the angle of incidence, r be the angle of refraction. Then from entry point to the point P, I'll write the Snell's law. Mu naught sine theta naught is equal to mu into sine theta. There's a medium through which it is entering is air, 1 into sine theta naught. What is the mu? Refractive index of the slab, A plus Bx. There's a one equation. Then, so here at point P, I'll draw a tangent to the path of the ray. It will make an angle theta. Now, theta is what? Angle of incidence at point P. At the same time, what is tan theta? Tan theta is a slope. So tan theta will write dy by dx. So I have the here sine theta equation. What is sine theta? Sine theta naught by a plus bx. Tan theta is there. So from sine theta, what we can write here? Sine theta, we can write this is sine theta naught. I think definitely we can calculate this. Then tan theta is what? Solving this, writing and integrating, we'll get the equation for the path. Here what is mu? Mu is varying along x-axis. If mu decreases, the ray what happen will take path like this. I'll show the rough diagram. This is for mu decreasing. As x increases, the value of mu naught will decrease. So again, how the boundary? The boundaries will be like this only. This is a boundary. Okay, fine. This is for decreasing. Mu decreases along x. Mu increases, the ray will bend. Mu decreases, the ray will bend like this. Again, the same methodology. Condition: the refractive index of the slab, it is varying along y-axis. The refractive index of slab, it is varying along y-axis. Then what conditions we have to work out? How the boundary? The boundary will be parallel to the y-axis. The boundary will be parallel to the x-axis, because the mu is varying along y-axis. The boundaries will be parallel to the x-axis. Then here the normal will be parallel to y-axis. Then the ray is entering here at the origin. Here this medium refractive index is air, it is 1. So angle of incidence theta naught. The ray water pen will bend in this way as mu is increased, because as the refractive index, as the ray moves from right to denser, it should bend towards normal. This is a normal. So the ray will trace a path like this. Then I'll apply Snell's law from the entry point to the point P. Mu naught sine theta naught equal to mu sine theta. What is theta? Angle of incidence at the point P. R is the angle of refraction. Then I'll draw a tangent at point P. It will make an angle alpha. Look at this, alpha and theta, they are not equal. Alpha plus theta is 90 degrees. Then here I'll substitute the variation of mu varies. I'll calculate the sine theta. Then what the slope? Tan alpha. Tan alpha should be equal to dy by dx. And what is alpha? 90 minus theta. So cot theta equal to dy by dx. So substitute from this sin theta, substitute cot theta. Then integrate, we'll get the path. There's a generalized approach. It may not be very important for JEE mains, only for advanced they'll ask you. That too they'll ask once. Just you should have the general mathematical approach here. And applying Snell's law from the entry point to the point P, where you are calculating the slope. Okay kids, now we have the next topic called as a prisms. Here there's a prism. This is called like a prism angle and is having refractoriness. These are called as a refracting edges, and the angle between the refracting edges will call angle of prism. This would be normal to the surface. I'm drawing it. There's a incident. The ray is incident, where I1 is angle of incidence. At M it will undergo the refraction. The ray, instead of going straight, will undergo refraction. Let R1 be the angle of refraction. Then again this ray, refracted ray, will encounter a boundary. This will be the normal, will undergo refraction, and this will become the emergent ray. We'll call this incident ray, refracted ray, and this is called like emergent ray. This angle of emergence I2. These are refracting angles. Then from this quadrilateral and triangle, R1 plus R2, here this R1 plus R2 should be equal to A. In almost all prism this will be there. This condition is this condition will be applicable. Now the ray is moving from rare to denser. So then what is the deviation at M? Angle of incidence minus angle of refraction. This is a deviation. So I1 minus R1. The ray here moving from denser to rarer. Then actually the ray wanted to go straight here, but it got deflected. So what is the deviation of I2 minus R2? So what is the total deviation suffered by the incident ray? Sum of deviation at M and N. So deviation at M, I minus R1. Deviation at N, I2 minus R2. R1 plus R2 is the substituting this. The deviation suffered by the ray passing through the prism given by I1 plus I2 minus A. This is called like a base of prism. This is called like angle of prism. These are called as refracting edges. This is a general idea. Try to remember. Almost in all prisms, this will become a general condition. Okay, now we'll discuss this minimum deviation one. As I plot this deviation as a function, means there's a deviation. Okay, we'll discuss about the minimum deviation. As I vary the deviation as a function of angle of incidence, the deviation curve will start decreasing. You take some one minimum value at angle of incidence I0, then again starts increasing. What is that angle of incidence? This one. This is the incident ray. This angle of incidence will vary. I'll measure the deviation as a function of this angle of incidence. Then the deviation here first will be maximum, then start decreasing, becomes minimum, again starts increasing. And we have to calculate the angle at which the deviation is minimum, that is I0 here. And at minimum deviation, R1 equal to R2, and angle of incidence equal to angle of emergence, which is equal to say I0. Then, so we are substituting all that. I'll get the mu equal to sine of A plus delta M by 2 by sine A by 2. A is the angle of prism, mu is the refractive index. This minimum deviation I'll calculate from the lab using prism table. I am able to predict the refractive index of the material of the prism. So this is one basic idea of the at minimum deviation, the refracted ray will be parallel to the base of the prism. This is a deviation curve, maximum deviation. At one angle, the angle of incidence when is equal to pi by 2. Here angle of incidence equal to pi by 2. Grazing incidence. it'll here if this is the grazing incidence, then this should be equal to critical angle R1 equal to C. This is a refractive angle, this is an emergent angle. Then what to measure this deviation of this will be the maximum. So what is one angle of incidence is equal to pi by 2. What about other angle? The other angle, when angle of incidence equal to V, grazing emergence. This will be grazing incidence. This will be grazing emergence. Again, the deviation will be maximum. So now, and it will be minimum deviation also. What about maximum deviation? One angle will be pi by 2. We'll calculate this value of U. I'll apply here mu sine R2 is equal to sine E. What is the angle here? Refractive index is 1 and the angle here is equal to sine E. Then mu what is R2 is equal to R2 is equal to R1 plus R2 is A, and this R1 should be equal to critical angle, so R2 equal to A minus C. Substitute here, solve this, mu sine A will expand here, sine A cos A sine C equal to sine A, mu sine A cos A is root of 1 minus sine square C. Sine of critical angle should be equal to 1 by mu. Okay, mu cos A root of 1 minus sine square, sine C will be 1 by mu. Solving this, we'll get expression for the E of mu sine A root of 1 minus mu square minus 1 minus sine square A sine A mu square minus 1 minus sine square A. This is the expression for the E value. So what is E will be sine inverse of this one. Substitute this, we'll get the maximum deviation. So there's one basic idea, sir, of the prism. Next topic we're having the small angle prism. There's the incident ray will undergo refraction, will get deviated. This will be the deviation. Then we know sine I1 equal to mu sine R1, mu sine R2 equal to I2. Then for small angles I1 equal to mu R1, I2 equal to mu R2. Substituting I1 equal to mu R1, I2 equal to mu R2, mu equal to R1 plus R2A. R1 plus R2A, so the deviation equal to mu minus 1 into A. There is a deviation for small angled prisms. This is applicable. So what is that small angle? This equation is valid only when the angle of prism varies anywhere between 12 to 0 degree, then this equation will be valid. Now, what is the approach? How to solve prism problems? The ray is the angle of incidence theta 1. The ray will first strike this surface, angle of incidence theta 1, angle of refraction theta 2, there is a refractive theta 3. Here the ray will undergo TIR, just TIR, so therefore this theta 3 should become equal to critical angle, and where sine 3 equal to 1 by mu. There is a condition. Then will undergo TIR. Again here it will undergo the the ray is incident at an angle theta 1, will undergo refraction, angle theta 2. Here the ray refracted ray will get incident at other phase, will undergo just TIR. Then for to undergo TIR, the angle of incidence here should be called critical angle. Then how that critical angle and the mu, because the other medium is air and refractive index mu, denser medium, refractive index mu, and the other medium is 1. So then sine critical angle should be equal to 1 by mu. So where all the critical angle is there, we can replace with sine inverse of 1 by mu. Then from the relationship, theta 2 to plus theta 3 should be equal to this angle of prism. Theta 3 plus theta 4 should be equal to this angle of prism. Yes. From the quadrilateral and the triangle. Then applying Snell's law, yes, 1 into sine theta 1 equal to mu sine theta 2. Theta 2 plus theta 3 equal to 1. Sine theta 3 equal to 1 by mu from the critical angle concept. Then theta 3 plus theta 4 equal to E2. Then mu sine theta 4 should be equal to 1 into sine theta 5. Solving this, we'll get this. So what is the deviation suffered by the ray here? The deviation here will be moving from rare to denser, theta 1 minus theta 2. It will undergo TIR. This will be pi minus 2 theta 3. Moving from denser to rarer, theta 5 minus theta 4. Like this will be the net deviation. Then any unknown things you can solve it. Just you have to apply the Snell's law of refraction here. Here the boundary where origin are parallel, the boundaries will be inclined. Now similarly, if the ray of light is incident here, will undergo refraction, will undergo TIR here, and again will undergo refraction. We'll write down some equation here. 1 into sin theta 1 equal to mu sin theta 2. Snell's law of refraction. Where it undergoes TIR, mu sin theta 3 equal to 1. Then mu sin theta 4 equal to sin 1 into sin theta 5. Theta 2 plus theta 3 equal to E2. Theta 3 plus theta 4 equal to E3. Then the net deviation moving from rare to denser. Theta 1 minus angle of incidence minus angle of refraction. And where it undergoes TIR, the ray wanted to go straight, so it got deviated. It wanted to go straight like this. There's a deviation here. How much deviation? 180 minus 2 theta 3. Here theta 5 minus theta 4. There's a net deviation. There's a general approach trying to develop. Now we'll discuss some. If a ray of light is incident on this normal phase, then it moves from rare to denser medium. So here it will undergo refraction. Then again it will encounter the boundary, it will undergo further refraction. Then if a ray is incident normally on this phase, then no refraction here. Then here refraction occurs and the ray will faint. If the ray enters at the base, here you can see like will undergo refraction. Again will undergo refraction. If the ray enters here like this, the ray enters here, will undergo refraction, and again will undergo refraction. The general idea you have to develop, if a ray is incident on the prism, how that refraction will take place. We can have a situation where the ray will be incident normally on one of the phases, will undergo TIR, will come here, will undergo refraction, will enter here. Here at this particular point you can see it is incident normally. This will be the angle of incidence. This is A. Here theta 1 you write it, theta 2, theta 3, theta 4. And the ray here goes undeviated. It will undergo TIR here. These are some angles, let me give it. Theta 1, theta 2, theta 3, and this angle is theta 4. Okay, again the same, the methodology is same. There's a mu, there's a surrounding medium is here. What is sin theta? Sin theta 1 equal to 1 by mu. And theta 1 equal to theta 2 because it will undergo TIR. Theta 2 plus theta 3 equal to E2. Then applying Snell's law here, mu sin theta 2 equal to 1 into sin theta 4. We can discuss the problem. If it undergoes TIR, bring the sin theta equal to mu condition, 1 by mu. Otherwise, Snell's law of refraction. Now, there's a generalized approach is what you have to develop. Just draw the prism, send rays in various directions and how it gets refracted. Then calculate the deviation. Okay, sir, what about deviation? Here no deviation. So the net deviation will be, here deviation will be the ray wanted to go straight. It got deviated here. Delta 1. Here the deviation there's a deviation. So the deviation will be 180 or pi minus 2 theta 1 plus theta 4 minus theta 3. And applying Snell's law where all needed. If prism is kept in a medium where the surrounding medium, the refractive index is mu naught, then what method we have to apply? The ray is incident here. Will undergo reflection. So will undergo refraction. Here this is the normal. The ray moving from rarer to denser. Also some it will be like it. Then again this will be normal. Then it will bend like this. Then this will be the incident ray, refracted ray. This is emergent ray. Angle of incidence theta 1, theta 2, theta 3, theta 4. Theta 2 plus theta 3 is equal to E. Applying Snell's law, mu naught, where the incident ray, mu naught sine theta 1 is equal to mu sine theta 2. Here mu sine theta 3 is equal to mu naught sine theta 4. If the prism is immersed in some liquid, okay, there is a basic method. Then what is the deviation? Deviation will define this as theta 1 minus theta 2 plus theta 4 minus theta 2. Theta 1 plus theta 4 minus of theta 2 plus theta 3 is again the same formula. Then what is the condition for minimum deviation? The minimum deviation will be mu by mu naught sine of A plus delta minimum by 2 sine A by 2. And at minimum deviation of the incident ray will be parallel to the base of the refracted ray will be parallel to the base of prism. This is a basic condition. By the angle of prism. So if surrounding medium is here, mu naught will be 1. If surrounding medium is there, the minimum deviation, you have to adjust the formula here. No need to bother anything. And at minimum deviation, the refracted ray here will be parallel to the base of the prism. This is one more basic condition which you have to remember. Next one, dispersion of light by prism. The refractive index of a material of prism will be dependent on the incident wavelength according to this formula, where A and B are constants for different material will be different. Lambda is the incident wavelength. For different wavelength, the mu of the material will be different here. Then for small angle prisms, so we define delta equal to mu minus 1. Okay, fine. Now we'll come for the spectrum. The wavelength of the violet will be less compared to green, compared to yellow, compared to red. There's a spectrum relationship, electromagnetic spectrum. Then the refractive index for the violet will be more. Lambda less, lambda V less than lambda R. So mu V should be greater than mu R. So the refractive index of the material for the different wavelength will vary in this way, the relationship. So mu for violet, the wavelength will be greater than compared to yellow, compared to red. Then the deviation, substitute here, the mu for violet is more, so definitely the violet will undergo more deviation than the red. So when a white light passes, visible light passes through the prism, it will split up into its constituents. That is called again dispersion. Splitting up of white light into its constituents is called as a dispersion. Then the deviation suffered by yellow color light will call mean deviation. Then the angular dispersion, the deviation suffered by the violet color minus red color, the difference of that will call angular dispersion. What is the deviation by yellow color light? UV minus 1 into U. UR minus A. What is A? A is the angle of prism. Here you can see this. Then UV minus mu R into A. Dispersive power, we define it angular dispersion by mean deviation. What is the angular dispersion? Delta V minus delta R by delta I. Solving this, I'll get the dispersive power. What do you mean by dispersive power? If greater the dispersive power, then you can see that the spectrum will be purer. You can see all the colors clearly visible and they are well separated, no overlap. Then the dispersive power is said to be more. Means it is able to split up white light into its constituents clearly. Greater the dispersive power, the more better spreading, no overlap, all the colors will be distinct. There's a dispersive power. So we need some materials where it should be very high dispersive power. And some materials, in some applications, the dispersive power should be minimum. So like this, we'll be designing that one, the optical instruments. And these are all some technical things which you should know. Next we have the deviation without dispersion. The white light is incident. Yes. The white light is incident here. This white light open will split up into its constituents. I'm just showing only three colors: red, yellow, violet. The red, yellow, and violet. Then again the next prism, the flint prism, it will again bend the ray of light such that the resultant emergent ray will be white light, and if you check that this resultant emergent white light will make some angle with the incident white light. So here the incident ray of the incident beam was white light, the emergent beam was white light, so therefore no dispersion, net dispersion is zero, but there's a deviation. So here we'll equate here now. The dispersion produced by the crown glass prism is mu v minus mu r into A. By the flint glass prism is mu v dash minus mu r dash into A. So the net dispersion is zero. I'll equate. I'll get the relation between A dash and A. This is one equation. Then how to calculate the deviation? The deviation produced by the crown plus flint. I'll add up here. Then this A dash will replace here now. Mu y minus 1. So here mu y minus 1 I'll take common. Then so we can bring the dispersive power, like a solve for dispersive power. The net deviation will be in terms of dispersive power of the prism. Mean deviation into 1 minus dispersive power of the crown by the flint. Omega dash dispersive power of the flint glass prism will be angular dispersion by mean deviation. Dispersive power of the crown prism will be angular dispersion by mean deviation. So we'll end up like this here. Okay, fine. So these things we have substituted. General formula. This is not there for JEE, not for JEE mains. Okay, fine. Only for advanced it is there. Next we have the dispersion without deviation. A white light is incident, will undergo dispersion. Again the flint glass will spread the light. So the emergent beam will get the violet light, will get the spectrum. So there's a spectrum. But if you look at the yellow color light will be parallel to the incident light. There will be yellow color light. The yellow color light will be parallel to the incident white light. So therefore the net deviation will be 0. So I'll equate the net deviation 0. Solving, we'll get this is a formula. Okay, fine. Then what about the net dispersion? I'll add up angular dispersion due to the crown and flint. I'll add up. Solving in terms of dispersive power, we'll get again omega. How you define? Delta V minus delta R by okay, this is a dispersive power. So these things we have replaced it here. Okay, fine. So these are the things you have to remember. Here, what is the dispersion without deviation? For incident white light, the resultant emergent will be, there will be a spectrum. And in that spectrum, the yellow color light will be moving parallel to the incident white light. That's why the net deviation is 0. You have to compare with this. Parallel. And there's a formula you have to remember. The net dispersion formula, mu I minus 1 into A into omega minus omega dash. If the prism is immersed in a liquid, then the minimum deviation, the refracted ray will be parallel to the base of a prism here, and the effective refractive index of the prism will be mu by mu naught sine of A plus delta minimum by 2 sine A by 2, where this deviation will be minimum. Okay, like this you have to remember condition. If there are two prisms are there next year, the ray is incident here, will undergo refraction, will come here. The first prism will produce a deviation, small angle prism, mu1 minus 1 into E1. And this emergent ray will pass through the second prism and it will undergo the deviation mu2 minus 1 into A. The net deviation is delta 1 plus delta 2. This is a net deviation. Next we have the hollow glass prism. Then if the ray of light is incident in it, will undergo refraction here, double refraction, and the emergent ray again will be parallel to it. Again will undergo double refraction and this will be the emergent ray. There won't be any deviation for hollow glass prism. The net deviation will be 0. There won't be any deviation for the hollow glass prism. Literally no use. So only we can see a lateral shift. Kids, we have the next topic, refraction at spherical surface. And this is one very small topic, and this will be a basic fundamental for the lens, the coming topic which is there. So a better understanding of this is needed. Okay, now I have there's an object, there's a boundary here. You can see some sort of like a cylindrical rod. We can call this like a rod. This we can call it as like a rod. Then here object kept in the rarer medium, refractive index N1, and there's a rod having the refractive index N2, let it be denser medium. So this particular ray of light is incident. This will become the normal. This will be the normal. The ray of light is moving from rarer to denser. Then it will slightly bend towards normal. This will be angle of incidence I. This will be angle of refraction. This will be angle of refraction R. Okay, fine. Now, the incident ray will make some angle with the axis. This is called like an axis. This is alpha. The refracted ray here will make an angle with the axis. There's a beta. The normal will make an angle gamma with the axis. There's an object distance, there's image distance, and there's a radius of curvature of this particular boundary. We'll apply the Snell's law, like a sin I equal to mu sin R, sin I equal to n1 sin I equal to n2 sin R. Then I is equal to what we can write in terms of the angles. R will be beta plus gamma. Okay, then using all that mathematics, finally we'll end up with this equation. This is for formula what we should use for the refraction at the spherical surface. What is N2? Refractive index of medium in which a refracted ray is present. N1, refractive index of medium where incident ray is present. V is the object image distance. U is the object distance. R is the radius of curvature of the boundary. Then the magnification, if any extended object is kept, here if any extended object is there. Then corresponding image will be like this. Then the magnification is given by N1, refractiveness of medium where incident ray is present, image distance by refractiveness of medium where refracted is present by object distance. There's a formula for magnification. And there's a formula. These are the two important formulas you have to remember. Okay, we'll see that how we can use this formula. I have the object here. A real object is kept here. The ray will be incident. There's a ray, there's an incident ray, there's a normal, there's an hemisphere. It will encounter a spherical boundary, here it will encounter the flat boundary. The ray moves from now right to denser, it will bend towards normal. Again, the ray is moving from denser to rarer, there's a normal, will bend away from normal, will meet at point I. We have to calculate this position, at what distance the image is formed. And this image will be real, if you consider. It is formed by the converging refracted rays. Then the formula mu, refractiveness of the medium where the refracted ray is present, mu by P1 I dash minus refractance medium where incident ray is present in air 1 by object distance P1O equal to mu minus 1. What is the radius of curvature of this? Will be positive now because we'll measure in the direction of incident ray. The distances measured in the direction of incident ray will be positive. Substituting all, what is P1O? P1O will be minus R because you have to measure P1O from here like this. And towards right is positive. We are measuring P1O towards left, therefore negative. R we are measuring radius in the direction of incident ray. So positive. And mu equal to how much? 1.5. Solving will get 1 by 2R. Solving I'll get P1 I dash equal to 9R. Here it will be formed. From here 9R. So from this plane surface it will be 8R. Now the ray will undergo refraction here. Then at P2, where the refracted ray is present in air 1 by P2I minus mu P2I dash equal 1 minus mu infinity. What is the radius of curvature of this plane surface? Infinity. Solving this, I'll get P2I equal to 16R by 3. What does it mean? The final image form will be real. Like this, we can trace out the image. If a point object is kept, point image will be formed. Next, instead of the same hemisphere, now the plane surface, plane boundary will be first. The object will face the plane boundary. Let's see what conditions will come. First, the ray, incident ray will undergo here, will undergo refraction at this point at the surface P1, at the boundary P1. The ray moving from right to denser. So the way the refracted ray is present in the denser medium 1.5 P1 I dash minus 1 by P1O. P1O will be negative because towards right we took positive. The refractor is present in the glass 1.5 minus. What is this boundary? Plane boundary. What is the radius of curvature of this? Will be infinity. Then solving will get P1 I1 dash minus. What do you mean by negative sign? The image will be here, will be virtual. What is this? This I dash, intermediate image. Now the ray again now will encounter one more boundary, moving from denser to rarer, so it will bend towards normal and we'll get the image here. So we'll calculate the position at what distance the image, final image I is formed. Again the refraction at curved surface P2, the refracted ray present in air, refractance 1 by P2I. The incident ray is, this will become incident ray present in the denser medium 1.5. Then at what distance the I dash is? P2I dash is how much? Equal to R plus 4.5R minus of 5.5R. Now the equation, how it has become 5.5, it will be like this. R plus 4.5R. Why negative sign? Because you are measuring P2I dash opposite to incident ray. R will be negative. You will measure radius in this direction, but the incident, there is a radius of curvature. Is measured opposite to incident, negative. Solving this, we'll get the P2R. P2I equal to how much? 5.5R. So this will be the real image. So this particular formula is applicable for both curved as well as the plane boundaries. Very important you have to remember. Half of the surface is silvered. A parallel beam of light is incident. First it will undergo refraction at P1. Here this surface P1. There's an incident ray, there's a refracted ray is present in the glass. So 1.5 P1 I1 minus 1 by infinity. Why infinity? Because the rays are coming from far away. Parallel beam of light. So what is the object distance? Will be infinity. 1.5 plus r. Solving, I'll get P1 I1 equal to 3r. Then the ray here now will undergo reflection. So this will behave like a concave mirror. So 1 by P2 I2 plus 1 by P2 I1 using mirror formula. So what is this? This is a mirror formula. One by P2 I2 plus 1 by P2 I1 equal to 1 by P2 C by R. What is P2 I1? P2 I1 will become equal to R. Substitute plus R. Focal length of this will be R by 2 minus R by 2. Solve it. P2 I2 equal to minus R by 2. So the image will be formed here. So after reflection, the rays will pass through this point, will again undergo refraction. Again refraction at P1. Now in what direction the rays are moving? Towards left. This will be incident ray, this will be refracted ray. Where the refracted ray present in a 1 by Pi3. Plus this will be incident ray, they are present in denser medium 1.5. Then what is the object? Object is here R plus 2R by 3. 1 minus 1 point. Solving this, I'll get P1I3 equal to minus 2.5R. So the final image will be here, which will be virtual. Like this, we can go for if the surface is silvered, a curved surface silvered. We'll take if the plane surface is silvered, what method has to be applied? The ray of light first will strike the curved surface. And here is what? The normal. This will be normal. So the ray is moving from rarer to denser. Will bend like this. So this will be the. So we'll apply the formula now. At P1. At P1 it will be towards left. At P1. Then the refracted ray is present in the denser medium. So mu into P1 I1 minus 1 P1O. So P1 I1 I am getting infinity. What do you mean infinity? The ray after reflection will become parallel. Possible. I brought this condition exclusively for that purpose. Will become parallel. The ray after reflection will become parallel. I will draw it. Parallel to the axis. Then we'll retrace path and it will come here. So where the final image? The final image will be formed at the object itself. After refraction should become parallel. The final image I2. Again the ray will retrace the path. Okay, these are some small ideas which you should be careful. So we'll start our last topic, what is the lens. Here, what all we discuss will be for principal rays or the rays which are incident very close to the optic axis. The first, this is called like a converging lens. What is a converging lens? If a ray incident in any direction, it will bend it towards the optic axis. This is called like a optic axis. Okay, fine. If a ray is incident parallel to the optic axis, after refraction will pass through the focus. Then, similarly, if a ray is passing through the focus, after refraction will become parallel to the optic axis. If the ray is incident at optic center, will go undeviated. This is a converging lens. It will bend the ray towards optic axis. Next we have diverging lens. If a ray is incident parallel to optic axis, after refraction will diverge from the focus. This is a diverging lens. If a ray is incident at the focus, after refraction will become parallel to the optic axis. If the ray passing through optic center will go undeviated. This is the diverging lens. We'll define like this. This is a converging lens. This will be a diverging lens. Okay, then further next, so this, what do you mean by focus? If object is at infinity, where the image will be formed, that is called like a second focus. If object at focus, where the image is formed at infinity, that will become first focus. Now, what all we discuss will be second focus. Second principal focus. So this focal length of the lens depends on what? For that we'll derive the lens maker formula. Very fundamental one. So I'll keep this a lens. Refractive index of the material of the lens is mu. The surrounding medium is air. So first we'll start with this one. The refraction object O is kept. This is the axis, or better called optic axis. And this is the optic center. Object O is kept here. The ray will undergo refraction, it will encounter spherical boundary, then undergo refraction, it wants to converge at I dash on the optic axis. Again it will encounter one more boundary. Then again it will undergo refraction, it will form the final image at I. And there is the object, there is the image. The object distance will indicate by U, the image distance as V. The radius of curvature of this will be like a R1. The radius of curvature of this will be R2. We are discussing this everything thin lens, not thick lens. Will be thin lens. Then the formula will be, first we'll apply the refraction spherical surface at point P1. This will be refracted rays present in the glass. So mu by V dash, the object distance will be V dash, minus 1 by object distance U equal to mu minus 1 into R1. Then again the refraction at this point, the refracted ray is present in air, 1 by V minus mu dash by V dash. This will become object for the second refractance, mu minus 1 minus R2. Then adding up these two will cancel out. So we'll get 1 by V minus 1 by U equal to mu minus 1 by R1. So this 1 by V minus 1 by U from length equation will become focal, 1 by a focal length. So the focal length of the like a lens depends on the refractiveness of medium, surrounding medium, and the radii of the curvature. Where R1, R2 you have to substitute this sign. If focal length positive, converging length, focal length negative will be diverging length. If surrounding medium is present, mu naught. If the lens is immersed in a liquid, if surrounding medium is present, then the ray will undergo here, will be incident, will undergo refraction. Then finally will meet here. Then what is surrounding medium? Mu naught. Then the same lens maker formula will be modeled. The surrounding medium will show in the denominator, mu by mu naught minus 1 by R1 minus 1 by R2. Like this we can calculate the focal length of the lens if it is immersed in some medium. If surrounding medium is here, this will become mu naught. Mu naught will be 1. image formation by the convex lens. There's a convex lens. Next, image formation by convex lens. If the object is at infinity, the rays will be incident parallel to the optic axis. After refraction, the rays will converge at a point, and that will be the focus. The second focus. The image will be formed at the second focus. If object at infinity, the image will be at second focus. Next, object at beyond 2f. Here 2f, f we have. It is beyond 2f. Where the image will be between f and 2f. And the image will be real. This is the image. This is the object. This is the object. This is the image. If object is between 2f, so one ray parallel to optic after refraction will pass through the focus. Other ray passing through optic center both will meet at this point and will get the image. So for object beyond 2f, the image will be between f and 2f, real, inverted and diminished. Next condition will take it. If object is at 2f, then where the image will be at 2f only. First, the ray will be incident parallel to optic. After refraction will pass through focus, will pass through point A dash. Then a ray passing through optic center will meet at point A dash. Both refracted rays are converging, so this will be a real image. If object at 2f, then image will be at 2f, real, inverted and same side. If object is between f and 2f. Then what about the image? Image will be at this particular point. And this will be the object. If object is between 2f and f, image will be beyond 2f, real, inverted and magnified. The ray diagram you can follow. One ray parallel to optic after refraction will pass through focus, other passing through optic center, both will converge, so therefore real image. If object at focus, ray parallel to optic after refraction will pass through focus, ray passing through optic center, both will be parallel to each other, the image will be at infinity. If object is at a distance less than f between focus and the pole, less than focal length, then final image will be formed. This will be virtual, erect and magnified. So for real object, the convex converging length will form real image, virtual image. Then for virtual object, we'll see what conditions will come. For virtual object, here there's a virtual object. The incident rays will try to converge. Then after refraction, because there's a convergence, they'll meet at a point. This will be the real image. So for convex lens, for virtual object, the image will be real, erect and diminished. See, one simple, if object and image on either side of lens, real object, real image. If object and image are on same side, real object, virtual image, virtual object, real image. So convex lens, what all it will form? For real object, real image. For real object, virtual image. Virtual object, real image. Virtual object, virtual image not possible. And this is the basic idea of the convex lens. Like this you have to remember. Okay, in very simplified short way I'm explaining. Try to grasp this. This is very, very important. Next we have the image formation by the concave lens or diverging lens. What do you mean by concave lens? It is called as diverging lens. A real object AB is kept. The ray incident parallel to optic axis after refraction will diverge from the focus. A ray passing through the optic center will go undeviated. Where these two rays intersect, there will be the position of the image, and the image will be virtual. So what about the image? Image will be virtual, erect and diminished. Anywhere you move object here, the image will be virtual, erect and diminished. Anywhere here. Next again, concave lens for virtual object. These are incident rays. They appear to converge at a point 2. Here, this one. Then after refraction, the refracted rays will diverge from a point. This will be virtual image. So virtual, erect and diminished. For virtual object, the image will be virtual, erect and diminished. This is one possible. Next one more condition. Same concave lens. There is a virtual object. Then these are incident rays. They appear to converge at a point. So therefore, there is a virtual object. After refraction, the rays will converge at a point. If the refracted rays converge, real image. If the refracted rays diverge, will be virtual image. So what is this? These are refracted rays. And what's happening? They're converging. So therefore we'll get a real image. And what is the real image? Image will be real, magnified and erect. So what is possible? What concave lens? A generalization of object image for real object. Virtual image. Virtual object. Virtual image. Virtual object, real image. There's a condition. Real object, real image, not possible. Like this, you have to remember the conditions. Next, we have the convex lens here. Convex lens. And we have kept a real object here. We'll see how where the object is. Let me keep it far away. We have to calculate where the image will be formed. The rays after refraction will form the real image. A ray parallel to the optic axis after refraction will pass through the focus. A ray passing through optic center will go undeviated. Ray passing through the focus will become parallel after refraction. All three rays will converge at a point. If these are refracted rays, if the refracted rays converge at a point, then it should be a real image. So for real object, the image will be real, inverted and diminished. Object beyond 2f, the image will be between f and 2f. Then as I move this object, it will also move. Then at one particular point, if object is at 2f, the image will be at 2f, will be real, inverted and same size. Then if object is between f and 2f, you can see this one. The height of object, height of the image. Height of the image is more. If the object is between f and 2f, this is 2f here, the image will be beyond 2f, real, inverted and magnified. If object is at focus, the image will be at infinity. Then if object is at less than focal length, less than between pole and focus, the image will be virtual. This is a basic idea. So as you move, so it will be like this. You can see this. Image is diminished. Then will become magnified. Then again this will become virtual. So this is one basic idea for the rays. This will be image formation. Okay, agreed. Now similarly we'll go for the concave lens. There's a concave lens or diverging lens. There's a first focus, this will be second focus, this will be first focus. And the object is kept far away. we'll see this one. The rays after refraction is a diverging lens, no? They'll get diverted. The image will be formed, the image will be virtual, erect, and diminished. As I move this object, look at the position of the image. The virtual image will be erect, virtual, erect, and diminished only. As we change the position of object, anywhere at focus also it will be virtual. So anywhere if you move object from minus infinity to the pole, what about the image? Image will move between focus to the pole, and it will be virtual, erect, and diminished. You can see clearly. This is about the diverging lens. You can see clearly here now. So what about at focus? I'll keep it focus. Then also it will be virtual image. If you keep object here, the image will be at infinity. If you keep object, this will be the first focus. This will be the second focus. Okay, this is about the diverging lens. You have to remember in this particular way. Now this is the converging lens. Focus, let it be 4 centimeter. Focus 4 centimeter, we assume like that. Then object is beyond 2f, where the image will be between f and 2f. 2f will be here. The image will be between 2 and between f and 2f. Then what about the object? For real object, extended object, the image will be real, inverted, and diminished. As I move this object, then the image what happens? Size will increase. Then when object at 2f, the image will be at 2f and will be of same size. The image will be real, inverted, and of same size. Beyond 2f, the image will be, you can see that object is beyond 2f, the image will be between f and 2f, real, inverted, and diminished. Then if object is between f and 2f, the image will be beyond 2f, real, inverted, and magnified. If object at focus, what about the image? Image will be at infinity. Next, if you see the object here, object between focus and the pole, the image will be virtual, erect, and magnified. Anywhere you can move here. And if object at pole, image will be at pole only. Okay, fine. So now we'll change the concave lens, we'll take it. Concave lens, the focus this will be the focus. No, this object. Object is far away. The image will be between focus and the pole will be erect, virtual, erect, and diminished. Anywhere you move this object, this is the image will move from, if you move object from far away till near focus, the image organ will move between focus and the pole only. And if object at pole, image will be at pole. Anywhere you can see that, anywhere. Even at focus, here we think that image at, no, the image will be virtual, erect, and diminished. The same condition on either side. These are some general things try to learn. Once you know this, rest all you can manage. combination of lenses. If two lenses are combined, there's an object O. So here the focal length of this lens is f1, this is f2. If only lens M were there, then the image would have formed at I1. Because of lens M, first the ray will undergo refraction. It wants to converge at I1. Again, it will undergo refraction due to lens N, and finally it will meet the optic axis at point. This is the final image. I want to replace these two lenses by single lens so that the position of image will not change. At what position the image is formed, at the same position the image should be formed. So what is the equivalent focal length? 1 by f equal to 1 by f1 plus 1 by f2. The reciprocal of focal length will call that as a power of lens. And this is called like a diopter. The unit for the power of lens will be diopter, not watt. And converging lens will be positive. Converging lens P1 will be positive. Power will be positive. Diverging lens power will be negative. Any lens, either concave or convex lens, you can replace here this one. If 2-3 lenses are there, you can replace with one equivalent lens. Now cutting lens, so there's a focal length. Radius of curvature is r. I'll cut this lens normal to the optic axis into two equal parts. Then the focal length of this will become f dash. Okay, we'll see how to calculate the focal length. First, what is the focal length of this? We'll calculate of the equiconvex lens. According to that will be f equal to mu minus 1. The ray will be first striking this surface. So radius of curvature of this will be plus r. Radius of this will be measured opposite to incident ray minus r. So f equal to mu minus 1 2 by r, or f equal to r by 2 mu minus 1. This is the focal length of this lens. When I cut it, so this will be the radius of this will be infinity, this will be positive. This is incident ray. Then 1 by f dash equal to mu minus 1. Radius of curvature r. The radius of curvature, this is infinity. Substitute, will get f dash. So from here, what is f dash equal to f? So when you cut lens normal to optic axis, the focal length will get doubled. Then if you cut into not symmetrical equal parts, the focal length of this will be 2f. The focal length of this will become, it's not a lens here now, because upper part will have focal length f. This section will have f dash, this section will be f. So this will become, this will become lens. This is not a lens, just some optical system. Will not become lens here, because upper part will have one focal length, this middle part will have one focal length, and lower part will have focal length f. There's a basic idea of the cutting of lens. Now, if we cut parallel to the axis here, I'll cut it. The radii will not change, and the mu of all the lengths is same. The radius of curvature has not changed. So then according to lens maker formula, mu minus 1 by r what is the focal length of each part will be same. So if you cut parallel to optic axis, the focal length will not change. Next we are having, if the lens is made up of different material, according to the this is the focal length. As the mu changes, focal length has to change. So here the lens is made up of 5 different material. Then the parallel beam of light, which is incident, will not converge at focus. It will spread here. So this will have one focal length. Second, yellow color will have one focal length, mu 2, because as the mu changes, focal length will change. So the rays will converge at different points. So how many different materials are there? 5 different materials. So how many images? 5 images will be formed. So the lens is made up of 5 different types of materials. 5 images will be formed. This will be more dangerous. So therefore, the lens which we are going to use in application should have the good purity. Otherwise, so due to impurities, the number of images will increase. we'll take the type of lens. The first equiconvex lens. Both radii will be same, converging lens. A parallel beam of light incident, it will converge at point. From the lens maker formula, 1 by f equal mu minus 1. The radius of curvature of this will be positive. Radius of curvature of this will be negative. Then solving this, f equal to r by 2 mu minus 1. Then there is the equiconvex lens. The ray of light is in the parallel top. After refraction will diverge from a point. Then radius of curvature of this will be negative. Radius of curvature of this will be positive. The incident ray on which first, or the surface on which incident ray is incident first, that should be substituted here. This will be next one. So if you get, this is a diverging lens, plano-convex lens. So the radius of curvature of this is plus r. This will be infinity. Solve it. Plano-concave lens. The radius of curvature of this will be negative. This will be infinity because plane surface. Substitute, will get the diverging lens. So equiconvex, equiconcave lens will have the radius focal length r by 2 mu minus 1. Plano-convex, plano-concave will have focal length r by mu minus 1. This is the converging lens. These two are the diverging lens. Next we have the positive meniscus. A ray of light is incident. After refraction will converge at a point. This will be the focus. Then radius of curvature of this is r. This is 3r. Substitute plus r. This also be plus 3r. Then how much will get? 3r by 2 mu minus 1. This will become positive meniscus will define. This will become positive meniscus. Then what will be negative meniscus? This is 3r and this r. The ray will first strike this surface. Radius of curvature negative. Next it will strike this surface minus 3r. So solving this, we'll say this one. This will become minus 1 by r plus 1 by 3r minus 2 by 3. So focal length of this will be minus 3r by 2 minus 1. Negative meniscus. This will be diverging length. Focal length positive, converging. Focal length negative means diverging. Next we'll take the silvered lens. There is a concave convex lens. The curved surface silvered. Radius of curvature are r1, r2. We have the values also here. We'll take help of this. Then the silvered lens. Lens plus curved reflecting surface. There's like a concave mirror. There's like a concave mirror. The radius of curvature we know r2, so we can calculate the focal length. What is the formula? 1 by f equal to 1 by fm minus 2 by fl. Then focal length of this r2 by 2 minus r2, because the ray is incident here like this. Towards right will be positive, so the radius of curvature will be negative. Minus 2 by, what is the focal length? What is the focal length of this will be? 1 by fl equal to mu minus 1 r1 r2. Substituting all with sign, I'll get focal length equal to 8 centimeters. Means I should replace with a concave mirror of focal length how much? 8 centimeters. Then if plano-convex, if a plano-convex lens is silvered, I'll silver the plane surface. Then plano-concave lens plus plane mirror. This should be equal to some mirror. So we'll calculate the focal length here. Here 1 by f equal to 1 by f minus 2 f. So what is the focal length of the plane mirror? Infinity. Focal length of this plano-concave lens 1 by fl equal to 2 into 1 by fl mu minus 1 minus 1 by r minus 1 by infinity. Solving this, I'll get the focal length. Focal length of this will be f equal to r by 2 mu minus 1. I got this positive. Positive means I should replace with a convex mirror. If you get negative, replace with a concave mirror. Next here, if curved surface is silvered, earlier plane surface, no? Now the curved surface is silvered. Then I'll split up this one, I'll break it up. Plano concave plus convex mirror. The effective focal length we have to calculate. 1 by Fm minus 2 by Fl. Now what is the focal length of this convex mirror? Radius of curvature of this r by 2. Is a convex mirror plus r by 2. What is the focal length of this plano concave lens? 2, 1 by mu minus 1, 1 by infinity minus 1 by r. Solving this, I'll end up with r by 3 minus 2 mu. So what is the focal length? Focal length, again I get positive, so I'll replace with a convex mirror. Then silver lens immersed in water. I'll immerse this in water. Then in that case what we should do, silver lens, I'll assume that made up of lens plus mirror. What about this lens? This lens is immersed in water. Then again the formula will be 1 by Fm minus 2 by Fl. Fm is how much? Radius of curvature of this r2 by 2, half of the radius of curvature. What is the focal length of the lens immersed in liquid? The surrounding liquid you have to substitute here. Mu of the lens, mu of the liquid minus 1, 1 by r1 minus 1 by r2. Solving this will get, if you get this focal length negative, replace with a concave mirror. If you get focal length this positive, replace with a convex mirror. Okay, agreed. So this is about the silver lens. No, if there's an object is there, there's a lens. The lens is moving. Velocity of the lens by VL object, and the image will be formed. Here image will be formed. Let VI be the velocity of image. There's an object distance, there's image distance. From the lens equation, 1 by V minus 1 by U equal to 1 by F. I'm differentiating this minus 1 by V square dV by dt. Derivative of this du by dt. Velocity of image with respect to lens. What is dV by dt? Velocity of image with respect to lens. What is du by dt? Because u is the object distance measured with respect to lens. So du by dt will be velocity of object with respect to lens. Then what is VILX? Velocity of image minus velocity of lens. What is VOLX? Velocity of object minus velocity of lens. How to calculate V by U? By using lens equation, because you know U and F, we can get the V. From the V, we'll substitute, we'll get the V by U whole square. Then we can calculate the velocity of the image. If the lens is attached, okay, fine, good. That you can apply it. So we'll get a situation where object and lens will be moving. This approach you have to develop. Next we have, if the medium on either side of lens is different, here mu1, mu2, mu3, we can't use lens maker formula. Again, come for refraction spherical surface. There's an incident ray. The ray will undergo refraction. The refracted ray is moving in the medium of refraction mu2, and the incident ray is in the medium of mu1. Applying the refraction spherical surface mu2 pi dash minus mu1. This is parallel beam of light. So where the object is at infinity, equal to mu2 minus mu1 by radius of curvature of this will be plus r1. Then again, this ray wanted to converge at I dash. Again, the refraction will take place here, will meet the optic axis at I. Then where the refracted ray is present now, in the medium of refractor mu3, this will become incident ray, this will be mu2. So the formula will be mu3 pi minus mu2 pi dash, mu3 minus mu2 by minus r2. Radius of curvature, this will be negative, because towards right is incident ray. Any distance measured opposite incident ray should be negative. R1 will measure like this. This is R1, I think. R2 will measure here. Center of curvature C1. How R2 is measured? R2 is measured opposite to incident ray. R1 measured in the direction of incident ray from the pole. Therefore, negative, there is a positive. Adding up these two, mu2 pi dash will cancel out. Mu3 pi, mu3 by pi equal to mu2 minus mu1 by r1, mu3 minus mu2 by r2, or 1 by pi. So where pi is equal to f. This will be the focal length. Mu2 minus mu1 by mu3 r1, mu2 minus mu3 by mu3 r2. Like this, if the medium on either side of lens is different, you should use this basic formula. Next one. So how to calculate the focal length of the lens by shift method. So I'll take the source extended object. This is screen. I'll keep the lens here. I'll move this lens and at one particular position I'll get a sharp image. Then I'll note down the position of objective 1 and V1. Similarly, further I'll move the lens. Again at one particular position of the object distance U2, I'll get the sharp image. How to know that there's a sharp image? The height of the object and the height of the images will be related by this equation. Then I'll note down the position of the lens at which a sharp image will be formed on the screen. The difference in those positions will call that as the shift. And what is the capital D? Distance between the source and the screen. This will be a fixed value. I know I'll measure the shift. I'll get the focal length of the convex lens. This is like a focal length of the lens by shift method. And when to measure H1, H2, the image should be sharp. How to know this is sharp? This H1, H2 and HO should satisfy this equation. Practically we find out the focal length of the convex lens using this method. Next, multiple lens problem. A parallel beam of light is incident on the convex lens. It will converge. The focal length is so adjusted that this will be F1. The rays wants to converge at point I1. Then the rays before converging at I1, they'll encounter the second lens and they'll become parallel. Because object kept at the focus for the diverging lens, image will be at infinity. Then if you check it, there's a diameter of the incident beam. There's a diameter of the refracted beam. So if I want to decrease the diameter of the beam, I can take help of this combination of lenses. Agreed? So these are some basic ideas, some very small things which will be more useful for you. Okay, kids, we had a discussion on the ray optics one shot. Almost all the ideas I explained here, and it is almost around 4 hours. So as I told you, like there's a lengthy chapter, lot of concepts are there, lot of ideas are there. Go through this video. If you go through this video 3, 4, 5 times, you'll get some basic picture. List out all the formulas. Remember them. Solve PYQ for JEE Mains. You can see the benefit in exam. As you solve PYQ, you will get confidence. Oh, I'm able to do it. Learning is needed. Learning and remembering. If you do these two things, it will be easier. So what about the advanced? You have to solve more number of numericals. I explained all the fundamental ideas, everything. Start solving problem. And as you start solving problem, your clarity will further increase. And there's nothing but the confidence. Okay, fine. So thank you for great support. I'll end up the session.